There's something undeniably humbling about staring up at the night sky, those countless pinpricks of light that have guided explorers, inspired poets, and sparked the curiosity of every civilization in human history. Yet, for all our advancements, the universe still holds secrets so profound they defy our wildest imaginations. What if everything we think we know about space, time, and reality itself is just a fraction of the story? Picture this: invisible forces stretching the fabric of the cosmos, particles that exist in two places at once, and regions of space where the laws of physics seem to rewrite themselves. These aren't scenes from science fiction, they're real, documented phenomena that scientists are grappling with right now. This journey isn't just about listing strange cosmic quirks, it's about unlocking a new way of seeing the universe. Over the centuries, humanity has clung to certain truths. Gravity pulls us down, light travels in straight lines, the cosmos operates on predictable rules. But what if those truths are merely illusions, or at best, incomplete? From the enigmatic pull of dark energy to the spooky interconnectedness of quantum particles, the deeper we look, the more the universe reveals its capacity to astonish. Each discovery peels back another layer, leaving us with more questions than answers, and that's the thrill of it. The cosmos isn't just stranger than we imagine, it's stranger than we can imagine. So why does this matter to you? Because these phenomena aren't distant abstractions, they shape the very reality we experience. The same quantum weirdness that baffles physicists might one day power unimaginable technologies. The same dark energy pushing galaxies apart could hold clues to the ultimate fate of everything. This isn't just science, it's a frontier where philosophy, wonder, and cutting-edge research collide. Whether you're a seasoned space enthusiast or someone who's never given astrophysics a second thought, these 42 phenomena will change how you see the night sky and your place within it. Ready to have your mind stretched? Let's begin. Imagine a universe where everything is expanding not just steadily, but faster and faster, like a runaway train with no brakes in sight. That's exactly what dark energy is doing right now, defying everything scientists once thought they knew about the cosmos. Back in the late 1990s, astronomers made a discovery so shocking it earned them the Nobel Prize. The expansion of the universe wasn't slowing down due to gravity, as everyone expected. Instead, something invisible and mysterious was pushing galaxies apart at an accelerating pace. This invisible force, dark energy, makes up a staggering 68% of the universe's total energy content. Yet we can't see it, touch it, or even detect it directly. It's like the universe's hidden engine working silently in the background, stretching the fabric of space itself. The implications are mind-bending. If this acceleration continues, distant galaxies will eventually vanish from our view, their light stretched beyond detection. The cosmos could end not with a bang, but with a cold, silent drift into infinite emptiness. But here's the real mystery: no one knows what dark energy actually is. Some theories suggest it's a property of space itself, a cosmic constant Einstein once proposed, then abandoned. Others speculate it could be an entirely new type of energy field, fluctuating and evolving over time. The truth is, every attempt to explain dark energy only deepens the puzzle, and that's what makes it so thrilling. This isn't just a gap in our knowledge, it's a glaring sign that the universe still has secrets we haven't even begun to uncover. What's at stake? The ultimate fate of everything. If dark energy's strength changes over time, it could rip galaxies apart, or even tear spacetime itself to shreds in a hypothetical Big Rip. Or it might fade away, allowing gravity to pull the cosmos back together in a dramatic collapse. Right now, we're left watching, measuring, and wondering. Dark energy isn't just reshaping the universe, it's reshaping our understanding of reality itself. And the next phenomenon might just hold the missing piece to this cosmic puzzle. While dark energy stretches the universe apart, its enigmatic counterpart, dark matter, holds the cosmos together in an invisible embrace. Picture a galaxy spinning so fast that its stars should fling outward like riders on a runaway carousel. Yet they don't. Something unseen, with gravity strong enough to bind them, lurks in the shadows. That's dark matter, a ghostly substance that makes up 27% of the universe, yet refuses to interact with light in any way. It doesn't shine, absorb, or reflect. It's the ultimate cosmic hide-and-seek champion. The evidence for dark matter is everywhere, written in the very fabric of space. When astronomers measure how galaxies rotate, they find stars on the outskirts moving just as fast as those near the center, defying the laws of gravity as we know them. Then there's gravitational lensing, the way massive objects bend light like a cosmic magnifying glass. Some galaxy clusters warp space so intensely that they must contain far more mass than what's visible. The conclusion: vast halos of dark matter surround galaxies, anchoring them with an unseen gravitational hand. But what is it? Scientists have proposed wild possibilities. Weakly interacting massive particles, or WIMP, are leading candidates. Hypothetical particles heavy enough to exert gravity, but nearly impossible to detect. Then there are actions, ultralight particles that might flit through space like quantum whispers. Some theories even suggest dark matter could be primordial black holes, remnants of the universe's fiery birth. Yet despite decades of searching, no experiment has definitively caught it. Underground labs, particle colliders, and space telescopes all hunt for clues, but dark matter remains stubbornly elusive. Here's the kicker: detecting it could rewrite physics. If dark matter is a new type of particle, it would prove there's more to reality than the standard model describes. It might even hint at hidden dimensions or parallel universes. And if we're wrong, if dark matter doesn't exist at all, then gravity itself must work differently on cosmic scales, upending Einstein's relativity. Either way, the answer will redefine our place in the universe. But dark matter isn't the only phantom haunting the cosmos. There's something even stranger, a phenomenon that bends not just space, but the very rules of cause and effect. Deep in the cosmic shadows, hidden behind the thick dust lanes of our own Milky Way, lurks a gravitational enigma so powerful it's dragging entire galaxies toward it, including ours. Astronomers call it the Great Attractor, and it's one of the most baffling mysteries in modern cosmology. Picture this: thousands of galaxies, including our local group, are all streaming toward a single point in space at millions of miles per hour, as if caught in an invisible river current. But what could possibly exert such a titanic pull? At first, scientists thought it might be a massive cluster of galaxies, a cosmic heavyweight with gravity strong enough to dominate our corner of the universe. And indeed, there is a concentration of matter there, the Norma Cluster, a dense gathering of galaxies about 250 million light-years away. But here's the catch: the math doesn't add up. The Norma Cluster is massive, but not nearly massive enough to explain the sheer scale of the motion we're observing. It's like blaming a pebble for creating a tidal wave. So what's really out there? Some theories suggest the Great Attractor is just the tip of the iceberg, a small part of an even larger structure, like the mind-boggling Laniakea supercluster, a galactic filament spanning 500 million light-years that our Milky Way calls home. Others propose even wilder ideas. Perhaps there's an unseen concentration of dark matter, or a gravitational anomaly left over from the early universe, warping space-time in ways we don't yet understand. The real challenge is that we can't see it clearly. The Great Attractor lies in what astronomers call the zone of avoidance, a region obscured by the dense gas and dust of our galaxy's disk. It's like trying to study a distant city through a thick fog. Only with advanced infrared and radio telescopes have we begun to pierce that veil, and every new observation raises more questions than answers. What makes this phenomenon so thrilling isn't just the mystery, it's what it reveals about the universe's structure. If the Great Attractor is part of something even larger, it hints at a cosmos far more organized and far stranger than we ever imagined. Galaxies aren't just scattered randomly, they're woven into an immense cosmic web, with threads of dark matter guiding their motion like invisible puppet strings. And if we're being pulled toward something we can't fully see or explain, what other colossal structures might be out there, hidden in the darkness? The universe, it seems, still has plenty of surprises up its sleeve. Einstein famously dismissed it as spooky action at a distance, a phenomenon so bizarre it seemed to mock the very foundations of physics. Yet decades later, quantum entanglement isn't just real. It's been demonstrated in labs across the globe, leaving scientists both awestruck and unsettled. Here's how it works when two particles become entangled. Their properties like spin or polarization lock together in an invisible bond, no matter how far apart they travel. Change one and its partner instantly responds, as if space and time don't exist between them. This isn't just theoretical. In experiments, scientists have separated entangled particles by over 1,200 kilometers, roughly the distance from New York to Chicago, and still observed this instantaneous connection. It's as if flipping a coin in Paris forced another coin in Tokyo to land the same way, defying every rule of classical physics. The implications are staggering. Either information is traveling faster than light, which relativity says is impossible, or our understanding of reality itself is missing a fundamental piece. What makes entanglement truly revolutionary is how it shreds our notion of locality, the idea that objects are only influenced by their immediate surroundings. Instead, the universe appears stitched together by invisible threads, with particles communicating in ways that transcend distance. Some theories suggest this could mean reality isn't as solid as we think, that at the quantum level, everything is interconnected in a vast dynamic web. And here's where things get even weirder. Black holes, those cosmic vacuum cleaners, might hold clues to how entanglement works on a grand scale. Theoretical physicists propose that the event horizon, the point of no return around a black hole, could be entangled with particles it emits, creating a bridge between the inside and outside. If true, this could mean entanglement isn't just a quantum quirk but a feature woven into the fabric of space-time itself. The practical applications are just as mind-bending. Quantum computers harness entangled particles to perform calculations at speeds impossible for classical machines, potentially revolutionizing fields from medicine to cryptography. Secure quantum communication could render hacking obsolete, with entangled photons creating unbreakable codes. Yet for all its promise, entanglement raises deeper questions. If particles can defy space and time, what other, impossible connections might the universe harbor? The answer could rewrite not just physics but our place within the cosmos. One thing's certain: the more we uncover about entanglement, the clearer it becomes that reality is far stranger and far more interconnected than Einstein ever imagined. And if this phenomenon stretches our understanding to its limits, just wait until we explore what lies beyond. Black holes aren't just cosmic vacuum cleaners, they're also the ultimate shredders of reality as we know it. At least that's what the infamous black hole information paradox suggests. and it's been tearing apart physicists' assumptions for decades. Here's the problem: quantum mechanics insists that information, the fundamental details of every particle state, can never be truly destroyed. Even if you burn a book, in theory, its information still exists in the ashes and smoke. But black holes, they're different. When matter falls in, it vanishes behind the event horizon, seemingly erased from the universe forever. Enter Stephen Hawking's groundbreaking revelation: black holes aren't entirely black. They emit radiation, now called Hawking radiation, slowly leaking energy and fading away over eons. But here's the catch: this radiation appears totally random, carrying no trace of the information swallowed by the black hole. It's like tossing a library into a furnace and getting only heat, no words. If the black hole eventually evaporates, where did all that information go? This contradiction pits quantum mechanics against general relativity in a battle with no clear winner. Some physicists refuse to accept information loss, proposing wild solutions. The holographic principle suggests that all the data swallowed by a black hole isn't lost. It's smeared across its event horizon like a cosmic hard drive, encoded in 2 dimensions instead of 3. Imagine a movie projected onto a flat screen, yet containing all the depth of a 3D world. If true, reality itself might be a hologram, with black holes as the ultimate storage devices. Then there's the firewall theory, a radical idea claiming the event horizon isn't the gentle boundary we thought. Instead, it could be a searing wall of energy, incinerating anything that crosses it. This would preserve information by preventing it from ever entering the black hole, but it also means astronauts wouldn't be gently stretched by tidal forces, as sci-fi suggests. They'd be vaporized instantly. Needless to say, this idea is controversial, but what if the truth is even stranger? Some theories speculate that black holes don't destroy information, they transport it. Wormholes, hidden dimensions, or even baby universes could be lurking inside, ferrying data to places we can't see. It's a cosmic escape hatch, preserving the universe's rules while keeping its secrets just out of reach. The stakes couldn't be higher. If black holes really erase information, our understanding of quantum mechanics is fundamentally flawed. If they don't, general relativity might need rewriting. Either way, solving this paradox could reveal the hidden architecture of reality itself. And if black holes are gateways, not graves, what else might be waiting on the other side? The answer could redefine not just physics, but the very nature of existence. Wormholes, those fantastical tunnels through space-time, aren't just the stuff of science fiction. They emerge straight from the equations of general relativity, courtesy of Einstein and his colleague Nathan Rosen. Picture space as a folded sheet of paper, with a wormhole acting as a cosmic shortcut, punching through the fold to connect 2 distant points in an instant. Need to travel across the galaxy. Instead of taking billions of years, a stable wormhole could get you there in minutes. The catch: actually building one is a nightmare of physics and imagination. First, there's the issue of stability. Natural wormholes, if they exist, would likely snap shut faster than you could say, interstellar road trip. That's where exotic matter comes in, a hypothetical substance with negative energy density that could prop the wormhole open like a cosmic jack. Unlike normal matter, which gravity pulls inward, exotic matter would exert negative pressure, pushing against collapse. The problem: we've never observed it, and quantum field theory suggests you'd need astronomical amounts of it, enough to wrap around a star. Then there's the radiation problem. Passing through a wormhole isn't exactly a smooth ride. Quantum effects near the throat, the narrowest part, could create intense tidal forces and high-energy particles, turning your journey into something resembling a trip through a particle accelerator. Even if you survived, the wormhole might destabilize behind you, stranding you in an unknown corner of the universe. But let's say we solve all that. The implications would be staggering. Wormholes could serve as time machines, with time dilation effects allowing travel to the past or future. They might even link parallel universes if theories like the multiverse hold water. The energy requirements are mind-boggling. Some calculations suggest you'd need the mass energy of an entire star just to keep a 1-meter-wide wormhole open for a second. Yet the mere possibility forces us to ask, if nature abhors a vacuum, does it also abhor shortcuts? Here's where it gets philosophical. Wormholes don't just challenge our engineering skills, they force us to rethink causality itself. A traversable wormhole could create paradoxes like the infamous grandfather paradox, where changing the past erases your own existence. Some physicists argue this means wormholes must be forbidden by some unseen law of physics. Others believe the universe might self-correct, allowing the wormhole but preventing paradoxes through quantum weirdness. The truth, we don't know. Wormholes exist firmly in the realm of maybe, a tantalizing blend of math and mystery. But their allure isn't just about shortcuts through space, it's about probing the boundaries of what's possible. If they're out there, hidden in the cosmic fabric, they'd be the ultimate testament to a universe far more connected and far more generous with its secrets than we ever dared to dream. And speaking of time, what if it's not the steady, unyielding river we think it is? What if it's something far stranger? Time isn't the steady, unchanging river we experience in daily life. It's more like a stretchy fabric, warping and bending under the influence of gravity and velocity. This mind-bending phenomenon, called time dilation, isn't just theoretical. Your GPS relies on it every day. Satellites orbiting Earth experience time slightly faster than we do on the surface, thanks to being farther from Earth's gravitational pull. Without constant adjustments, your navigation would be off by miles within minutes. But this is just the tame version of time's flexibility. Near a black hole, time distortion becomes extreme. Imagine two astronauts. One stays far from the black hole while the other plunges toward the event horizon. To the distant observer, their companion appears to move in slow motion, like a video stuck buffering. Clocks near the black hole would tick agonizingly slow compared to those farther away. In fact, at the event horizon itself, time would appear to stop completely from an outsider's perspective. Yet for the astronaut falling in, their experience would feel entirely normal until tidal forces, not time, became their immediate concern. This isn't just a black hole quirk. Speed does the same thing. The famous twin paradox illustrates this perfectly. If one twin rockets away at near light speed and returns, they'll have aged less than their Earth-bound sibling. At 99% light speed, a 5-year trip for the traveler could mean decades or even centuries passing back home. Time dilation forces us to confront a startling truth. There is no universal now. Every observer's experience of time is personal, shaped by their motion and the gravity they're immersed in. So what does this mean for the future? If humans ever travel to other stars, time dilation could become both an obstacle and a bizarre advantage. A crew heading to Proxima Centauri at near light speed might experience the journey as a few years, while Earth sees it as a 4.5-year wait each way. For more distant stars, the effect grows extreme. Reach the Andromeda galaxy at such speeds, and you might age only a few decades, while 2.5 million years pass in your absence. The ultimate one-way trip with no home to return to. But here's where it gets truly wild. If time is this malleable, what else about our reality might be an illusion? The Multiverse Theory suggests that every quantum decision spawns alternate timelines, infinite versions of reality where time unfolds differently in each. Some physicists speculate that black holes might even be gateways to these other universes, their extreme time dilation acting as a cosmic buffer between realities. Others propose that the very fabric of spacetime could be littered with naturally occurring time warps, regions where the flow of time accelerates or crawls like eddies in a river. The implications ripple far beyond astrophysics. If time isn't absolute, then causality, the idea that cause must precede effect, might not be as ironclad as we think. Quantum experiments already show particles influencing each other instantaneously across vast distances, challenging our linear view of time. Could extreme time dilation create scenarios where effect precedes cause? The math allows it, even if our intuition rebels. One thing's certain: time dilation shatters the illusion of a predictable, clockwork universe. It reveals a cosmos far more dynamic and interconnected than Newton ever imagined, where gravity and motion don't just bend space, they twist time itself into knots. And if time can stretch like taffy near a black hole, what other cosmic illusions are we taking for granted? The answer might lie in the quantum realm, where particles defy not just time, but the very notion of objective reality. The idea of a multiverse, that our universe might be just one bubble in an infinite cosmic foam of realities, sounds like pure science fiction. Yet some of the most respected theories in physics point to this mind-bending possibility. Take cosmic inflation, the theory that our universe underwent exponential expansion in its first fraction of a second. Here's where it gets wild. If inflation can happen once, why couldn't it happen repeatedly, spawning countless universes with different physical laws? Picture a boiling pot of water with bubbles forming endlessly, each bubble a self-contained universe forever out of reach from the others. String theory adds another layer to this cosmic tapestry. It suggests the existence of up to 10 to the 500 possible universes, each with unique constants of nature. In some, gravity might be too weak to form stars. In others, atoms could be unstable, preventing matter from coalescing. This landscape of possibilities could explain why our universe seems so finely tuned for life. If every possible configuration exists somewhere, it's no surprise we find ourselves in one where conditions allow galaxies, planets, and conscious observers like us to exist. Quantum mechanics offers yet another multiverse angle. The many worlds interpretation proposes that every quantum decision spawns branching timelines. Flip a coin and in one universe it lands heads, in another tails. Multiply this by every quantum event since the Big Bang, and you get an unfathomable tree of realities where every possible outcome plays out. There's a version of you who became an astronaut, another who moved to Bali, and countless others whose lives diverged in ways you can't begin to imagine. But here's the catch: we have no direct evidence for any of this. The multiverse remains a speculative framework, a way to make sense of gaps in our understanding. Critics argue it's not science if it can't be tested, while proponents counter that some versions might leave faint imprints like cold spots in the cosmic microwave background from collisions with other universe bubbles. The debate forces us to ask, is the multiverse a profound insight into reality's structure, or a philosophical placeholder for mysteries we can't yet solve? Before we get lost in infinite realities, let's return to something more tangible: the expansion of our own universe. Because whether or not parallel worlds exist, the one we inhabit is stretching before our very eyes, carrying galaxies away from us like leaves on a cosmic river. And that expansion might hold clues to the grandest question of all: how this story ends. Imagine meticulously measuring the same room with two different rulers, only to get wildly different results every time. That's essentially the crisis cosmologists are facing with the Hubble tension, a stubborn discrepancy in measuring how fast the universe is expanding. On one side, we have the Planck satellite's observations of the cosmic microwave background, the afterglow of the Big Bang, suggesting an expansion rate of about 67 kilometers per second per megaparsec. On the other, telescopes like Hubble study pulsating stars and supernova, pointing to a faster rate of around 73. At first glance, the difference seems small, but in cosmology, even a few kilometers per second can unravel our understanding of reality. So what's going on? One possibility is that our measurements are flawed. Perhaps dust or unknown stellar physics is skewing the data, but after years of cross-checking, the gap refuses to close. That leaves two far more exciting options. Either we're missing a piece of the cosmic puzzle, or the laws of physics themselves need rewriting. Some theorists propose dark radiation, an exotic, fast-moving particle from the early universe, could be altering the expansion rate. Others speculate that dark energy isn't constant but evolves over time, subtly tweaking the universe's growth. Then there's the neutrino wildcard, these ghostly particles which stream through you by the trillions every second might have unexpected properties. If neutrinos interact with dark matter or possess unusual masses, they could influence the universe's expansion in ways we haven't accounted for. It's a long shot, but in science, long shots often lead to breakthroughs. The stakes immense. If the Hubble tension reveals new physics, it could reshape everything from particle theory to the ultimate fate of the cosmos. Or it might expose gaps in our observational methods, forcing us to rethink how we measure the universe. Either way, this isn't just academic, it's a reminder that the cosmos still holds cards close to its chest, and the next discovery might not just resolve the tension, it could tear the rulebook apart entirely. But this cosmic detective story doesn't end with expansion rates. There's another anomaly lurking in the shadows, one that challenges not just how the universe grows, but how it's structured. Every second, trillions of nearly invisible particles streak through your body like cosmic ghosts, neutrinos, the universe's most elusive messengers, born in the hearts of stars, supernova, and even nuclear reactors. These phantoms travel at near light speed, barely interacting with matter. But here's the twist, they don't stay the same. Neutrinos pull off a quantum magic trick called oscillation, spontaneously morphing between three types: electron, muon, and tau, as they race through space. It's as if a blue car turned red, then green without slowing down. This shape-shifting act isn't just a curiosity, it shattered decades of assumptions. For years, physicists assumed neutrinos were massless like photons, but oscillations proved otherwise. If neutrinos can change flavors, they must have mass, however vanishingly small. The discovery forced a rewrite of the standard model of particle physics, the rulebook governing the universe's building blocks. Suddenly, there was a crack in the foundation, hinting at physics beyond our current understanding. The implications ripple across cosmology. Neutrinos are so abundant that even their tiny masses influence how galaxies cluster. They may hold clues to why the universe is made of matter instead of antimatter, a mystery known as leptogenesis. Some theories suggest heavy, right-handed neutrinos yet to be detected could explain this cosmic imbalance. Others propose neutrinos interact with dark matter, acting as invisible bridges between the known and unknown. Detecting these phantoms is a feat of ingenuity. Giant underground tanks like Super Kamiok and in Japan wait for the rare moment a neutrino collides with an atom, releasing a faint flash of light. Ice Cube in Antarctica uses a cubic kilometer of glacial ice as a detector, catching neutrinos from distant galaxies. Each observation peels back another layer of the neutrino's secrets, but the biggest surprise might still be ahead. Could neutrinos be the key to a unified theory of physics? Their bizarre behavior straddles the quantum and cosmic realms, threading through black holes, supernova, and the Big Bang itself. They're reminders that even the most subtle forces can shape the universe in profound ways. And if something as slight as a neutrino's mass can upend our models, what other invisible players might be hiding in plain sight? The answer could lie even farther out in the faint glow of the universe's edge, where light from the first stars carries whispers of a time before galaxies. But to hear those whispers, we'll need to tune into the oldest signal in existence. The cosmic microwave background is more than just a snapshot of the universe's infancy. It's a cryptic message from the dawn of time, etched in microwaves. This faint glow, the afterbirth of the Big Bang, blankets the cosmos at a frigid 2.7 degrees above absolute zero. For decades, scientists assumed it would be nearly uniform, a smooth tapestry of radiation. But when satellites like Planck mapped it with unprecedented precision, they found something unsettling. The background isn't perfectly even. Tiny temperature fluctuations, hot and cold spots no larger than 1 part in 100,000, dot the sky like cosmic freckles. These imperfections shouldn't exist in a perfectly uniform early universe. So what carved them into the fabric of reality? The leading theory points to quantum fluctuations, microscopic ripples in space-time that emerged in the universe's first fleeting moments. Imagine a calm pond suddenly struck by invisible raindrops. Each drop creates a tiny wave, and as the pond expands, those waves stretch into larger patterns. In the infant cosmos, these quantum ripples were stretched by inflation, the universe's explosive growth spurt, imprinting themselves as temperature variations in the cosmic microwave background. Over billions of years, those subtle density differences seeded the galaxies and voids we see today. It's an elegant story, except some of the anomalies refuse to fit. Take the cold spot, a bizarre region spanning nearly 1 billion light-years where the background radiation is significantly chillier than its surroundings. It's too large and too cold to explain with standard quantum fluctuations. Some theorists propose it's the bruise left by a collision with another universe, a multiverse bubble brushing against our own. Others suggest it's a cosmic texture, a defect in space-time structure left over from the universe's violent birth. Then there's the axis of evil, an eerie alignment of hot and cold spots that defies the assumption the universe is isotropic, the same in all directions. If true, it implies the cosmos has a preferred orientation, a cosmic North Star that shouldn't exist in a universe born from chaos. The implications are staggering. If these anomalies aren't statistical flukes, they could rewrite the story of cosmic origins. Perhaps inflation wasn't the only force shaping the early universe. Some models propose a bounce, a cycle of contraction and expansion predating the Big Bang that left scars in the microwave background. Others speculate that dark energy or exotic particles interacted with the newborn cosmos, twisting its structure in ways we're only beginning to decipher. But the most radical idea, that we're seeing evidence of a multiverse. If other universes exist beyond our own, their gravity could tug on ours during inflation, leaving faint fingerprints in the cosmic microwave background. It's like finding footprints in the sand when you thought you were alone on the beach. The challenge is separating cosmic coincidence from genuine revelation. Future telescopes, like the European Space Agency's proposed CMB-S4, aim to map the background with even finer detail, hunting for patterns that could confirm or dismantle these bold theories. What makes these anomalies so thrilling isn't just their mystery, it's their defiance of the expected. The cosmic microwave background was supposed to be the ultimate confirmation of the Big Bang model. Instead, it's become a puzzle box hiding clues to realities we never imagined. If the early universe wasn't the smooth, uniform soup we thought, what other surprises lurk in those ancient microwaves? The answer might not just reshape cosmology, it could redefine the very nature of existence. And if the universe's first light holds such secrets, what might its oldest structures reveal? From the cosmic web's vast filaments to the enigmatic voids between them, the universe's architecture is anything but random. But to understand how it all fits together, we'll need to venture into the darkest, emptiest places in existence. The Higgs field isn't just some abstract concept, it's the invisible scaffold holding reality together. Without it, electrons would zip around at light speed, atoms would never form, and the universe as we know it would dissolve into chaos. But what if this cosmic cornerstone isn't as stable as we think? Lurking in the equations of quantum physics is a nightmare scenario called vacuum decay, a process so destructive it could rewrite the laws of physics in an instant. Here's how it works. Imagine the Higgs field as a marble resting in a valley, representing our current false vacuum state. It seems stable, but quantum theory suggests there might be a deeper valley, a true vacuum with lower energy. If the marble somehow tunnels through the hill into that lower valley, the collapse would spread outward at light speed, rewriting the fundamental constants of nature in its wake. One moment, stars and planets exist, the next, they're erased, replaced by a new reality where chemistry, gravity, even light itself might operate under alien rules. The trigger could be as random as a quantum fluctuation in some distant galaxy. Once the bubble forms, there'd be no warning. By the time we saw the wall of annihilation approaching, it would already be too late. The light showing its arrival would be racing just ahead of the destruction itself. Scientists calculate the odds are astronomically low. The universe has lasted 13.8 billion years without collapsing, after all. But the mere possibility forces a chilling question. Are we living on borrowed time in a cosmic house of cards? This isn't just theoretical doom-mongering. Particle colliders like the Large Hadron Collider briefly create conditions hotter than the early universe, leading some to speculate, though without evidence, that high-energy experiments could theoretically nudge the Higgs field toward catastrophe. Most physicists dismiss this fear, pointing out that cosmic rays have bombarded Earth with far higher energies for eons without triggering vacuum decay. Still, the idea lingers in the scientific imagination, a reminder that the universe's stability might be more precarious than it appears. What makes vacuum decay uniquely terrifying isn't just its inevitability if triggered, but its existential indifference. Unlike asteroid impacts or supernova, there's no way to shield ourselves from a law of physics rewrite. No technology could outrun it, no warning system could save us. The universe wouldn't end with fire or ice, but with a silent, instantaneous reconfiguration, a cosmic reboot where the rules we rely on simply vanish. Yet paradoxically, this doomsday scenario highlights something profound about our place in the cosmos. The fact that we can even contemplate such esoteric threats speaks to humanity's extraordinary capacity to decode the universe's deepest secrets. And while vacuum decay remains speculative, it underscores a humbling truth. Reality as we experience it might be just one precarious arrangement in a vast landscape of possible physics. But if the Higgs field isn't what keeps you up at night, consider a far more immediate cosmic threat, one that's already left scars across the galaxy. Gamma-ray bursts are the universe's most violent explosions, capable of sterilizing entire solar systems in seconds. And unlike vacuum decay, we know these celestial death beams are real. Gamma-ray bursts are the universe's deadliest fireworks, blinding flashes of energy so intense they outshine entire galaxies for a few terrifying seconds. Packing more power than our sun will emit in 10 billion years, these cosmic explosions come in two lethal varieties: short bursts lasting less than 2 seconds, arise when two neutron stars spiral into each other in a catastrophic dance, merging into a black hole. The longer bursts, lasting minutes, stem from hypernova-supernova on steroids, where collapsing massive stars fire jets of radiation at nearly light speed. Either way, the result is the same: a focused beam of gamma rays capable of stripping atmospheres from planets thousands of light years away. Earth isn't immune. Geological records hint that our planet may have been grazed by a gamma ray burst around 450 million years ago, possibly triggering the Ordovician mass extinction that wiped out 85% of marine species. The telltale signature, a sudden depletion of ozone, followed by a spike in mutated fossil spores, evidence of radiation bombardment. Today, astronomers monitor nearby stars like WR-104, a ticking time bomb 8,000 light-years away. If it goes hypernova and its jet aligns with Earth, the burst could deliver a radiation dose equivalent to 1,000 chest X-rays per second across half the planet. So why are we still here? Pure cosmic luck. Gamma-ray bursts are rare in our galactic neighborhood, and their beams are narrow, like aiming a flashlight across a dark room. The odds of one hitting Earth head-on are slim, but there's another tantalizing possibility. Life might not have originated here at all. The theory of Panspermia suggests that microbial hitchhikers could have ridden comets or interstellar dust, seeding Earth after a nearby gamma-ray burst sterilized its surface. It's a poetic twist. The very violence that makes the universe lethal might also distribute life's building blocks like celestial dandelion seeds. What's truly mind-bending is how these bursts shape the cosmos. They may have set hard limits on where life can arise, clearing out entire galactic regions like a cosmic reset button. Yet they also forge heavy elements, gold, platinum, uranium, in their neutron star collisions, scattering the ingredients for planets and life across the void. Gamma-ray bursts are both destroyers and creators, reminders that the universe thrives on extremes. And if life can survive their fury, what other impossible feats might be written in the stars? Could life itself be the universe's greatest traveler? The theory of Panspermia turns our Earth-centric view of biology upside down, proposing that life didn't originate here at all. It arrived here, hitching rides on comets, asteroids, or even interstellar dust. Picture this: a microscopic organism frozen in the heart of a wandering space rock, surviving the vacuum of space for millions of years before crashing into a young Earth, seeding our planet with the first sparks of life. It sounds like science fiction, but the evidence is mounting, and it's rewriting our understanding of where we come from. Take extremophiles, Earth's toughest life forms. These microscopic marvels thrive in boiling hydrothermal vents, acidic lakes, even the crushing pressures of the deep ocean floor. Some, like the bacterium Deinococcus radiodurans, can survive lethal doses of radiation that would vaporize most organisms. Others endure decades of complete dehydration, reviving like cosmic time capsules when water returns. If life can withstand such extremes on Earth, why couldn't it survive a journey through space? Experiments on the International Space Station have confirmed that certain bacteria and lichens can cling to the exterior of spacecraft, exposed to vacuum and solar radiation, yet still remain viable. Suddenly, the leap from Mars to Earth, or even between star systems, doesn't seem so far-fetched. Then there's the chemical trail. Astronomers have detected complex organic molecules, the building blocks of life, floating in interstellar clouds, clinging to comets, and embedded in meteorites. Amino acids, the same compounds that form proteins in our bodies, have been found in the Murchison meteorite that fell to Australia in 1969. Even more astonishing, the Rosetta mission discovered glycine, a simple amino acid in the coma of Comet 67P. These findings suggest that the ingredients for life aren't rare. They're scattered across the cosmos like cosmic breadcrumbs, waiting for the right conditions to assemble into something greater. But if life can hop between worlds, where else might it have taken root? Europa, Jupiter's icy moon, is a prime candidate. Beneath its frozen crust lies a global ocean, one holding twice as much liquid water as all of Earth's seas combined. Hydrothermal vents on its seafloor, much like those nurturing life in Earth's darkest depths, could provide energy and chemistry for alien ecosystems. Even Saturn's moon Enceladus sprays plumes of water into space, and Cassini's flybys revealed they're laced with organic compounds. These ocean worlds might not just host life. They could be way stations in a galactic relay, swapping microbes via meteorite impacts over billions of years. The implications are staggering. If life travels, then Earth may not be a solitary oasis, it could be part of a vast, interconnected biosphere spanning star systems. A single microbe surviving a journey from Mars could explain why life appeared on Earth so quickly after the planet cooled. Some scientists even speculate that life's building blocks might be universal, with DNA-like molecules emerging wherever conditions allow. We could be the descendants of cosmic nomads, our ancestry written in stardust and comet ice. Yet panspermia isn't just about the past, it reshapes how we search for life today. If organisms can spread between worlds, then finding life on Mars or Europa might not mean discovering a second Genesis, but rather tracing our own extended family tree. The next time you gaze at the night sky, consider this. We might not be alone because we never were. The universe could be teeming with distant cousins, all sprung from the same ancient interstellar seed. And if life thrives in the darkest oceans of our solar system, what wonders might lurk in the unknown seas of distant exoplanets? The answer could be closer than we think, or already here, waiting to be recognized. Beneath Europa's frozen, cracked surface lies one of the most tantalizing mysteries in our solar system. A global ocean, not of ice, but of liquid water, kept warm by the relentless gravitational tug of war between Jupiter and its moons. This isn't some shallow, subsurface pond. We're talking about a body of water twice the volume of Earth's oceans, hidden under an icy shell up to 25 kilometers thick. But here's what makes it truly extraordinary. Hubble Space Telescope observations have caught glimpses of towering plumes erupting from Europa's south pole, spraying water vapor hundreds of kilometers into space. These geysers are like cosmic smoke signals, hinting at the ocean's presence and possibly its habitability. What could fuel life in such an alien environment? Sunlight never pierces Europa's ice, but that doesn't mean energy is absent. On Earth, hydrothermal vents at the bottom of our oceans support thriving ecosystems entirely independent of the sun. Giant tube worms, blind shrimp, and heat-loving microbes thrive in these pitch-black oases, drawing energy from chemical reactions between seawater and molten rock. Europa's seafloor, churned by tidal heating, could host similar vents, offering both warmth and the raw materials for life. The chemistry is already tantalizing. The moon's icy surface is streaked with reddish-brown fractures, likely salts and organic compounds, ingredients that, mixed with water and heat, might spark life's emergence. Upcoming missions like NASA Europa Clipper, launching in 2024, aim to settle the debate. This spacecraft won't land, but it'll conduct 45 close flybys, mapping the ice shell, measuring the ocean's depth, and even sampling those plumes for organic molecules. Imagine detecting amino acids or lipids in those ejected particles. It wouldn't confirm life, but it would scream that Europa has all the right pieces. Meanwhile, the European Space Agency's JWST mission will study Europa alongside Jupiter's other icy moons, painting a broader picture of these watery worlds. But let's pause on that word life. Not intelligent civilizations, not even fish or algae, but microbes. If Europa hosts organisms, they'd likely resemble Earth's extremophiles, creatures thriving in conditions once thought uninhabitable. Take Desulforudes audaxviator, a bacterium found miles underground in South African mines, surviving on nothing but the radioactive decay of rocks, or Culwellia psychoerythrea, a microbe that flourishes in Arctic ice at temperatures that would shatter glass. These aren't fringe oddities, they're proof that life clings to even the harshest niches. If Earth's extremes can harbor such tenacity, why not Europa's dark, briny depths? The implications ripple far beyond biology. A living Europa would suggest that habitable environments aren't rare, they're everywhere, waiting beneath the ice of moons like Saturn's Enceladus or Neptune's Triton. It would mean our solar system could host multiple origins of life, independent of Earth, and if life can arise twice in one star system, the galaxy might be teeming with it. But there's a darker twist. Europa's ocean is likely ancient, perhaps as old as the solar system itself. If we find nothing there, it could mean life's emergence is far rarer, or that something lethal lurks in these subsurface seas. For now, Europa remains a locked treasure chest, its secrets sealed under ice. But with every plume spotted, every mission planned, we're inching closer to answering one of humanity's oldest questions. Are we alone? The answer might not come as a radio signal from distant stars, but as a microbe frozen in a grain of ice, whispering that life is far more adaptable and far more widespread than we ever dared to dream. And if Europa's ocean holds such promise, what might we find when we turn our gaze to the even stranger, more distant worlds of the outer solar system? Deep in the crushing darkness of the Pacific Ocean, where scalding water meets toxic chemicals, an entire ecosystem thrives without a single ray of sunlight. These are the extremophiles, nature's ultimate survivors, rewriting the rules of where life can exist. Take the Pompeii worm, a creature that basks in water heated to 80 degrees Celsius while anchored to volcanic vents that spew sulfur and heavy metals. Or consider Deinococcus radiodurans, a bacterium so resistant to radiation it can endure doses 5,000 times stronger than what would kill a human, earning it the nickname Conan the Bacterium. These organisms aren't just biological oddities, they're proof that life clings to existence in places we once considered utterly inhospitable. Their resilience shatters our Earth-centric assumptions about habitability. For decades, scientists defined the Goldilocks zone, that narrow orbital band where a planet is neither too hot nor too cold for liquid water. But extremophiles laugh in the face of such limitations. There's Halobacterium, thriving in Utah's Great Salt Lake at salinity levels 10 times higher than seawater, or Psychrobacter, multiplying happily in Antarctic ice at -20 degrees Celsius. Even more astonishing are the acidophiles like Ferroplasma acidomanus, which dissolve metals in sulfuric acid as corrosive as battery fluid and call it lunch. If life can flourish in boiling acid, frozen wastelands, and radioactive sludge, then the universe's real estate for potential biology just exploded. This revelation sends shockwaves through the search for extraterrestrial life. Mars, once written off as a barren wasteland, now looks like prime extremophile territory. The red planet's underground lava tubes could shelter microbes from deadly surface radiation, while its briny subsurface lakes detected by Mars orbiters might host salt-loving organisms akin to Earth's halophiles. Even the planet's infamous perchlorates, toxic chemicals that litter the soil, could be energy sources for specialized bacteria. After all, we've found Earth microbes that metabolize arsenic and uranium. Why couldn't Martian life adapt similarly? The implications stretch beyond our solar system. Europa's icy crust and Enceladus's hydrothermal vents suddenly seem like galactic hotspots rather than frozen dead zones. Exoplanets orbiting red dwarfs, once dismissed for tidal locking and violent flares, might harbor life in their twilight zones or subterranean oceans. Even Venus's hellish clouds, where temperatures and pressures mimic Earth's surface, could float acid-resistant microbes like aerial plankton. The extremophile paradigm doesn't just expand the habitable zone, it obliterates the concept entirely, suggesting life might lurk in the unlikeliest corners of the cosmos. But here's the twist: extremophiles might not be the exception. They could be the rule. Life on Earth likely began in extreme environments, hydrothermal vents or volcanic pools, meaning our ancestors were extremophiles. Modern organisms like us, thriving in mild conditions, might be the outliers. This flips the script on astrobiology. Instead of hunting for Earth twins, we should be probing the galaxy's most punishing environments: methane lakes on Titan, the subsurface oceans of dwarf planets like Ceres, or even the hydrocarbon dunes of Pluto. The discovery of a single microbe on Mars or Europa would confirm life isn't a fluke. It's a cosmic imperative, blooming wherever chemistry and energy intersect. And if extremophiles teach us anything, it's that the universe's creativity dwarfs our imagination. After all, we're the ones who labeled their homes extreme. To them, it's just another day in the neighborhood. The real question isn't whether life exists elsewhere, it's how many times and in how many forms the universe has whispered, adapt. And if life can conquer such brutal environments, what might intelligence look like in those worlds? Could there be civilizations thriving in conditions we'd consider unthinkable? The answer might lie not in the stars but beneath our feet, or more precisely, beneath the icy crust of a moon we've only begun to explore. Mars keeps teasing us with a gas that shouldn't be there: methane, flickering in and out of detection like a cosmic Morse code. On Earth, 95% of atmospheric methane comes from living organisms, from burping cows to underground microbes. So when Curiosity rover sniffed traces of it in Gale Crater, with levels mysteriously spiking and plunging with the seasons, it sent shockwaves through the astrobiology community. But before we declare microbial Martians, there's a catch. Methane can also form without life, when water interacts with certain rocks deep underground. The debate isn't just academic. It's a high-stakes puzzle where every clue could rewrite our place in the universe. Let's break down the evidence. Orbiting spacecraft like ESA's Mars Express first detected methane plumes back in 2004, with some concentrations reaching 45 parts per billion. Not much by Earth standards, but startling for a planet presumed geologically dead. Then came Curiosity's ground truth, measurements showing baseline methane levels around 0.41 parts per billion, punctuated by sudden tenfold spikes. These bursts don't linger, they dissipate within weeks, suggesting something is actively producing or releasing the gas right now. The most tantalizing pattern. Peaks during Mars' northern summer, when subsurface ice might melt just enough to release trapped methane, or awaken dormant organisms, but non-biological explanations are equally compelling. A process called serpentinization, where water reacts with olivine-rich rocks, can generate methane abiotically. Mars' crust might also contain clathrates, ice like cages trapping ancient methane formed by volcanic activity billions of years ago. Even meteorites deliver organic compounds that could break down into methane under ultraviolet light. the European-Russian trace gas orbiter threw a wrench into the mystery by finding no methane in Mars' upper atmosphere, suggesting surface-level detection might stem from localized, short-lived sources rather than a planet-wide phenomenon. Here's where it gets fascinating. Distinguishing biological from geological methane might require catching it in the act. Future missions like NASA Mars Life Explorer could drill 2 meters below the surface beyond the reach of destructive radiation to hunt for microbial communities or their chemical fingerprints. Imagine a scenario where we find methane alongside complex organic molecules like ethane or propane, a combination far more likely from biological processes. Or we might uncover isotope ratios in the methane itself. Life tends to favor lighter carbon isotopes, leaving a distinct signature. The stakes transcend Mars. If methane comes from microbes, it proves life isn't Earth's exclusive miracle, it's a cosmic inevitability. But if geology alone explains it, Mars becomes a cautionary tale of how easily a habitable world can wither. Venus drives this point home. Orbital data suggests it once had shallow oceans for 2 billion years before runaway greenhouse effects boiled them away. Mars may have followed a different path. Its core cooled, its magnetic shield failed, and solar radiation stripped its atmosphere molecule by molecule. Either way, both planets whisper the same warning: habitable windows can slam shut. What makes the methane mystery so compelling isn't just the search for Martians, it's the forensic reconstruction of an entire world's rise and fall. Every whiff of gas, every isotopic ratio, is a clue in a billion-year cold case. And whether the answer points to geology or biology, one truth remains: Mars was never just a red rock. It's a graveyard of possibilities, and its secrets are still breathing. Venus wasn't always a hellscape. Beneath its thick, sulfuric acid clouds lies a chilling cautionary tale, a planet that might have once been Earth's twin, with oceans, temperate climates, and perhaps even conditions ripe for life. Today, its surface bakes at 460 degrees Celsius, hot enough to melt lead, under an atmosphere 90 times denser than Earth's, where carbon dioxide traps heat like a suffocating blanket. This is the runaway greenhouse effect in its most extreme form, and it raises an unsettling question: could Earth, with its own rising CO2 levels, someday follow the same path? The story of Venus's transformation reads like a slow-motion disaster. Billions of years ago, the young sun was dimmer, and Venus may have had liquid water pooling on its surface. But as the sun grew brighter, Venus's proximity, just 70% of Earth's distance, tipped the balance. Water vapor, a potent greenhouse gas, built up in the atmosphere, trapping more heat and evaporating more water in a vicious cycle. Temperatures soared, oceans boiled away, and volcanic activity released even more CO2. Without Earth's plate tectonics to recycle carbon back into the crust, Venus's atmosphere became a pressure cooker, its surface a scorched wasteland. Earth's climate models now use Venus as a stress test. While our planet's distance from the Sun and active carbon cycle make a full Venus-style collapse unlikely, the parallels are unnerving. The same feedback loops that doomed Venus water vapor amplification, methane releases from thawing permafrost, and CO2 from burning fossil fuels, are already at work here, just on a slower scale. Venus shows us where unmitigated greenhouse effects lead, not just to warmer summers, but to a point of no return where the climate spirals out of control. Yet there's a crucial difference: time. Venus had no one to intervene. Humanity, armed with data from probes like Japan's Akatsuki and ISA's upcoming Envision mission, can still alter Earth's trajectory. Studying Venus's atmosphere reveals how clouds reflect or trap heat. how superrotation whips winds at hurricane speeds, and how sulfur compounds create reflective haze, clues that could refine our own climate strategies. Some scientists even proposed terraforming Venus by blocking sunlight or converting its CO2 into oxygen. Though these remain speculative, the real lesson isn't doom, it's urgency. Venus proves that climate change isn't about saving the planet, it's about saving our place on it. Earth won't become Venus tomorrow, but the mechanisms are eerily similar. The difference is choice. Every ton of CO2 we cut, every forest we preserve, buys time to avoid slipping toward that tipping point. Venus stands as a silent sentinel, a reminder that planets can change, and not always for the better. But while Venus warns of atmospheric apocalypse, the cosmos holds other stellar oddities far stranger than a greenhouse gone wild. Some stars don't just burn, they explode, collapse, or vanish into darkness, rewriting the rules of physics in their wake. Neutron stars are cosmic overachievers, stellar corpses so dense they pack more mass than our Sun into a sphere no wider than Manhattan. Picture squeezing Mount Everest into a teaspoon. That's the kind of crushing gravity we're talking about. Born from the explosive deaths of massive stars, these remnants defy logic. Their cores are a quantum playground where matter gets weird, protons and electrons merge into neutrons, creating a superfluid so flawless it flows without friction, while the crust crystallizes into a lattice harder than diamond. But the real magic happens when neutron stars collide. In 2017, astronomers witnessed history. Two neutron stars spiraling toward each other 130 million light-years away. As they merged, the event dubbed a kilonova unleashed a gamma-ray burst and ripples in space-time called gravitational waves, detected by LIGO and Virgo observatories. The aftermath was even more startling. For the first time, telescopes caught the glow of heavy elements like gold, platinum, and uranium forged in the cosmic furnace. That single collision produced an estimated 10 Earth masses of gold alone, solving a mystery that puzzled scientists for decades, where the universe's heaviest elements come from. But neutron stars aren't just element factories. Their extreme environments push physics to its limits. Magnetic fields around magnetars, a neutron star subclass, are so strong they could strip data from a credit card halfway to the moon. Some spin hundreds of times per second, their surfaces whipping around at a quarter the speed of light. And deep inside, the pressure might crush neutrons into exotic states, quark-gluon plasma, or even stranger forms of matter we've yet to name. What's truly humbling is how these dead stars illuminate the living universe. Their collisions map the cosmic web structure through gravitational waves, while their precise pulses serve as interstellar lighthouses for navigation. Yet for all we've learned, neutron stars guard secrets that could rewrite physics. What happens at their cores? Could quark stars or strange matter exist? Each observation peels back another layer, revealing a universe far wilder than we ever dreamed. And if a single collision can seed the cosmos with gold, what other wonders might be hiding in the echoes of these celestial titans? Kilonovae aren't just spectacular light shows they're the universe's ultimate alchemists, transforming the debris of dead stars into precious metals in a heartbeat. When two neutron stars spiral into each other, their collision unleashes energy so extreme they briefly outshine entire galaxies. But the real magic happens in the aftermath. As the stars merge, their cores already denser than atomic nuclei get squeezed even further, triggering a runaway nuclear reaction that forges elements like gold, platinum, and uranium in seconds. A single kilonova can produce enough gold to outweigh entire planets, scattering these heavy metals across space in glowing, radioactive clouds. For decades, scientists puzzled over where half the periodic table's heaviest elements originated. Now we know they're stardust forged in the most violent reunions imaginable. The process is a masterclass in cosmic chemistry. As the neutron stars collide, tidal forces rip them apart, ejecting neutron-rich material at relativistic speeds. In this superheated soup, rapid neutron capture, or the R process, takes over. Atomic nuclei gulp down free neutrons faster than they can decay, bulking up into heavyweight elements like iodine, thorium, and even uranium. The entire sequence unfolds in less time than it takes to blink, yet its fallout lingers for millennia. Spectroscopic analysis of kilonova afterglows reveals telltale signatures of these metals, their light tinged with the fingerprints of freshly minted stardust. But kilonovae aren't just one-trick ponies. Their explosions also create bizarre gravitational wave signatures, ripples in space-time that detectors like LIGO can pick up. These waves carry clues about the neutron star's masses, spins, and even the nature of matter itself. Some theories suggest that the densest mergers might collapse into black holes instantly, while others leave behind a hypermassive neutron star, a fleeting, unstable object teetering on the brink of collapse. The energy released in these events is so immense it can power particle jets moving at 99% the speed of light, beaming gamma rays across the cosmos like interstellar lighthouses. Yet neutron stars have even stranger tricks up their sleeves. Enter magnetars, the universe's ultimate magnetic monsters. These neutron stars boast magnetic fields 1,000 trillion times stronger than Earth's, so powerful they can atomize molecules from halfway across the solar system. A magnetar's crust, under such titanic strain, occasionally cracks, triggering starquakes that release flares of X-rays and gamma rays. In 2004, a magnetar 50,000 light-years away unleashed a burst so bright it temporarily ionized Earth's upper atmosphere, despite being far beyond our galaxy's edge. What makes magnetars truly unsettling is their potential as cosmic time bombs. Some lurk in our galactic backyard, like SGR 0185-20, just 15,000 light-years distant. A direct hit from one of its hyperflares could strip ozone from our atmosphere, triggering mass extinctions. But these objects also serve as natural laboratories, their extreme conditions letting us test physics in ways no Earth-bound experiment could. Quantum effects normally confined to subatomic scales become macroscopically visible in a magnetar's grip, warping the very structure of space-time around them. The more we study these stellar oddities, the clearer it becomes. Neutron stars are more than relics, they're active players in shaping the cosmos. Their collisions seed galaxies with the building blocks of planets and life, while their magnetic fury sculpts the space around them. And if their secrets seem extreme, just wait until we explore the even more enigmatic objects they sometimes leave behind. Black holes so dense they vanish from the visible universe altogether. Magnetars are the universe's ultimate cosmic tantrum, throwers neutron stars with magnetic fields so intense they bend the very rules of physics. Imagine a magnetic force 1,000,000,000 times stronger than Earth's, capable of erasing every hard drive on our planet from 50,000 light-years away. These stellar zombies don't just sit quietly in the void, they crack under pressure, literally. When their crusts snap from magnetic strain, the resulting starquakes unleash bursts of X-rays and gamma rays violent enough to light up entire galaxies. In 2004, one such flare from magnetar SGR 1806-20 halfway across the Milky Way briefly outshone the full moon, despite being invisible to the naked eye. So how do these magnetic monsters form? The story begins with death and rebirth. When a massive star, at least 8 times heftier than our Sun, exhausts its nuclear fuel, it collapses under its own weight in a cataclysmic supernova. Most neutron stars are born spinning fast, but magnetars take it further. If the dying star's core is rotating especially rapidly, and its magnetic field gets twisted like a cosmic spring during collapse, the result is a magnetar, a neutron star with magnetic energy dialed up to apocalyptic levels. Think of it as stellar dynamo effect gone haywire, where the star's original magnetic field gets compressed and amplified to ludicrous extremes during its violent birth. Their power isn't just theoretical. Magnetar flares can strip atmospheres off nearby planets, and their magnetic fields are so strong they distort the quantum vacuum around them, creating bizarre conditions where light itself splits into two paths, an effect usually only seen in lab experiments with ultra-strong magnets. Even more unsettling, some magnetars exhibit anti-glitches, where instead of speeding up during rotational hiccups like normal neutron stars, they suddenly slow down. It's as if their internal superfluid core is fighting against their own crust, a cosmic tug of war we're only beginning to understand. Yet for all their fury, magnetars are fleeting by cosmic standards. Their magnetic fields decay over a few millennia, leaving behind a quieter neutron star. That means every magnetar we see is relatively young, a screaming infant in stellar terms. And that raises a chilling question. If one formed closer to Earth, say within a few dozen light years, a single flare could fry satellites, knock out power grids, and bathe the planet in DNA-shredding radiation. The Carrington event of 1859, a solar storm that set telegraph wires ablaze, would pale in comparison. But here's the twist: magnetars might also be cosmic benefactors. Some scientists speculate their eruptions could kickstart chemical reactions in interstellar clouds, seeding the building blocks for new stars and planets. Their magnetic fields might even funnel cosmic rays, shaping the ecology of entire galaxies. Like so much in the universe, destruction and creation are two sides of the same coin. And if magnetars teach us anything, it's that the cosmos doesn't just harbor beauty, it thrums with forces so raw they redefine the word extreme. Now consider this: if a dying star's spin can birth something as bizarre as a magnetar, what other stellar oddities might be lurking in the dark, waiting to shatter our assumptions? The answer could lie in the quietest corpses of all, black holes so dark they swallow even the memory of light. Supernova should be the universe's most symmetrical explosions, stars collapsing inward with such force that the rebound ought to blast material outward in a perfect sphere. Yet time and again, telescopes capture dying stars erupting in chaotic, lopsided tantrums, hurling debris in jagged jets and leaving behind mangled remnants that defy expectations. The Crab Nebula, the glowing wreckage of a supernova observed in 1054, tells this story vividly. At its heart spins a pulsar, a neutron star rotating 30 times per second, but it's not centered neatly within the nebula. Instead, it's racing outward at over 1,000 kilometers per second, trailing a wake of twisted magnetic fields and high-energy particles. This off-kilter behavior isn't a fluke, it's the rule. So why do stars explode so messily? The answer lies in their turbulent interiors. In their final moments, massive stars become roiling cauldrons of instability. Convection currents churn like boiling water, while neutrinos, those ghostly particles produced in the core, escape unevenly, carrying away energy in fits and starts. This creates pockets of weaker and stronger pressure, like a balloon with thin spots bursting irregularly. But the real game changer is rotation. A spinning star flattens at its poles and bulges at its equator, and when the core collapses, this asymmetry amplifies. The star's magnetic fields, wound tight by the spin, channel the explosion along their lines, funneling debris into opposing jets like cosmic fire hoses. The result, a supernova that looks more like a squashed firework than a perfect sphere. These crooked explosions leave fingerprints everywhere. Supernova remnants like Cassiopeia, a show debris cloud stretched into bizarre shapes, with clumps of iron and silicon flung far beyond where symmetrical models predict. Even the neutron stars left behind often get kicked by the imbalanced blast, hurtling through space at breakneck speeds. The Crab Pulsar's wild motion isn't an anomaly, it's a testament to the violence of its birth. But the implications go beyond stellar forensics. Asymmetrical supernovae are cosmic sculptors, shaping how heavy elements spread through galaxies. Uniform explosions would distribute metals evenly, but lopsided ones inject them in concentrated streams, creating pockets of enriched material where new stars and planets might form. They might even solve a long-standing puzzle: why some neutron stars spin so fast. A off-center explosion could transfer angular momentum to the newborn pulsar, spinning it up like a flick top. The chaos isn't just destruction, it's creation with personality. And if stars can't even die predictably, what other cosmic rules might be more like loose guidelines? The universe, it seems, has a flair for the dramatic. The Crab Pulsar isn't just a cosmic oddity, it's a high-speed enigma, spinning so fast it completes a full rotation every 33 milliseconds, sending beams of radiation slicing through space like a lighthouse on overdrive. Discovered in 1968, this neutron star became the first object ever linked to a historical supernova, the brilliant explosion recorded by Chinese astronomers in 1054. Today, it's one of the most intensely studied objects in the sky, not just for what it reveals about stellar corpses, but for the bizarre hiccups in its otherwise precise rhythm. Pulsars are often called the universe's most accurate clocks, their radio pulses arriving with metronomic regularity. But the Crab Pulsar has a habit of glitching sudden, unpredictable jumps in its spin rate that last mere seconds before settling back into rhythm. These glitches aren't random quirks, they're windows into the star's turbulent interior. Picture a neutron star's crust as a rigid lattice of atomic nuclei, floating atop a superfluid sea of neutrons. As the star slows over time, the superfluid, unaffected by friction, spins faster than the crust. When the mismatch becomes too extreme, the superfluid transfers energy to the crust in a violent surge, like a pot of water suddenly boiling over. The result, a glitch that speeds up the pulsar's spin by a fraction of a second before friction restores equilibrium. But here's where it gets stranger. The Crab Pulsar doesn't just speed up, it also slows down more abruptly than expected between glitches, as if something inside is dragging against its rotation. Some theories suggest vortices in the superfluid might occasionally pin to the crust, creating temporary resistance. Others propose that the star's monstrous magnetic field, 1 trillion times stronger than Earth's, could be warping the superfluid's flow. Every glitch is a cryptic message, hinting at physics we can't yet replicate on Earth. And then there's the radiation. The Crab Pulsar doesn't just pulse in radio waves. It's a powerhouse of X-rays and gamma rays, with a wind of charged particles so intense it lights up the surrounding nebula like a fluorescent sign. This wind is fueled by the pulsar's magnetic field, which acts like a cosmic generator, accelerating particles to near light speeds. Yet even here, surprises lurk. Occasionally, the pulsar emits gamma-ray flares so powerful they temporarily outshine its usual output by a factor of 5. These eruptions defy existing models. No one knows how the pulsar suddenly concentrates so much energy into such bursts. What makes the Crab Pulsar so captivating isn't just its defiance of expectations, it's the way it bridges the known and the unknown. On one hand, Its pulses are so regular that astronomers once considered using pulsars as interstellar GPS beacons. On the other, its glitches and flares remind us that neutron stars are anything but simple. They're dynamic, seething objects where the laws of quantum physics play out on a macroscopic scale. And if something as seemingly straightforward as a spinning star can harbor such complexity, what other cosmic certainties might be ripe for rethinking? Yet for all its mysteries, the Crab Pulsar faces an unlikely rival in precision: atomic clocks here on Earth. These human-made marvels, which rely on the vibrations of cesium or rubidium atoms, are so accurate they'd lose less than a second over millions of years. In a cosmic irony, our terrestrial timekeepers now outpace even the universe's most rhythmic stars, proof that sometimes the greatest discoveries aren't just found in the heavens, but built in labs. Still, the Crab Pulsar holds one unbeatable record. It's a natural laboratory, offering glimpses into extremes of density, magnetism, and gravity we'll never recreate on Earth. And every time it glitches, it's not just breaking rhythm, it's sending us a coded telegram from the heart of a star. Time crystals sound like something ripped from a science fiction novel, matter that doesn't just exist in space, but ticks rhythmically through time like an eternal clock. Unlike ordinary crystals where atoms arrange themselves in repeating patterns across 3 dimensions, time crystals break the most fundamental symmetry of all: time itself. Their atoms oscillate between states at fixed intervals, perpetually cycling without any energy input, as if the universe granted them a loophole in the laws of physics. This isn't theoretical musing. In 2016, researchers at the University of Maryland and Harvard brought these bizarre structures to life inside quantum labs, using chains of ytterbium ions and diamond impurities to create the first working prototypes. The secret lies in what physicists call time translation symmetry breaking. Normally, the laws of physics don't care when you perform an experiment, whether it's Monday or Friday. Gravity works the same. But time crystals flout this rule. When nudged by a laser pulse, their atomic structures don't just respond once. They enter a loop, flipping back and forth between 2 configurations indefinitely, like a pendulum that never winds down. What's truly bizarre is that this motion requires no energy after the initial kick, defying our expectation that all systems must eventually settle into equilibrium. It's as if these crystals found a way to tap into the universe's hidden metronome. Practical applications are already shimmering on the horizon. Time crystals could revolutionize quantum computing by acting as ultra-stable memory units, immune to the decoherence that plagues qubits. Their rhythmic precision might also unlock new ways to synchronize quantum networks or even probe the fabric of spacetime itself. Some theorists speculate that time crystals could mimic exotic states of matter predicted to exist near black holes, where gravity warps time into strange new geometries. But here's the tantalizing question: if matter can tick like a clock, what other phases lurk undiscovered? Quantum foam, a seething, fractal-like structure theorized to exist at the Planck scale, might be next. Picture spacetime not as a smooth continuum, but as a bubbling cauldron of virtual particles popping in and out of existence. If time crystals rewrite the rules of matter, quantum foam could upend our very notion of reality's building blocks. The frontier of physics isn't just expanding, it's pulsating, twisting, and rewriting itself with every discovery. And if time crystals teach us anything, it's that the universe's playbook is far stranger than we ever dared to dream. If you could peer into the fabric of spacetime with a microscope powerful enough to see the Planck scale, a distance so tiny it's a billionth of a trillionth of a trillionth of a meter, you wouldn't find smooth emptiness. Instead, you'd witness a seething, chaotic froth where the very concepts of here and now dissolve into uncertainty. This is quantum foam, a turbulent sea of virtual particles that blink in and out of existence so fast they defy measurement, borrowing energy from the vacuum itself before vanishing like cosmic fireflies. The idea emerged from combining quantum mechanics with general relativity, and what it reveals is unsettling. At its core, the universe might not be a continuous, flowing reality, but a churning ocean of infinitesimal, flickering bubbles. The implications shatter our classical intuition. Imagine spacetime not as a still pond, but as boiling water, with tiny bubbles of energy constantly forming and popping. These aren't metaphorical bubbles, they're real fluctuations where particle-antiparticle pairs emerge from nothingness, annihilate, and return their borrowed energy to the vacuum, all within fractions of a second. Gravity, it turns out, isn't immune to this chaos. At these scales, the smooth curvature of spacetime predicted by Einstein's equations gives way to wild, unpredictable twists and kinks. It's as if the universe's stage is made of shifting sand, not solid ground. This foaminess isn't just theoretical. Some models of loop quantum gravity propose that spacetime isn't infinitely divisible, it's pixelated, woven from discrete, indivisible chunks at the Planck scale. Think of it like a digital image. Zoom in far enough, and the smooth picture breaks into individual pixels. If true, this would mean motion itself isn't perfectly continuous. Objects don't glide through space but move in tiny, quantum jumps. Even time might tick forward in discrete steps like frames in a cosmic film reel. But how do we reconcile this with the vast, smooth cosmos we observe? The answer lies in scale. Just as ocean waves appear smooth from a distance despite being made of trillions of jostling water molecules, spacetime's foaminess averages out over larger distances, leaving the illusion of continuity. Yet there are ways to test this wild idea. Some scientists hunt for subtle distortions in high-energy gamma rays traveling across the universe. If spacetime is foamy, these rays should scatter slightly, like light passing through frosted glass. Others look for anomalies in the spin of distant pulsars, which might reveal spacetime's granularity tugging on their rotation. The stakes are profound. If quantum foam is real, it could bridge the gap between quantum mechanics and gravity, two theories that have stubbornly resisted unification for a century. It might also rewrite our understanding of black holes, where foam like turbulence near the singularity could prevent the infinite densities general relativity predicts. Even the Big Bang might not have been a single point, but a quantum fluctuation in an older, foamy spacetime. What's truly humbling is how quantum foam forces us to confront the limits of human perception. We evolved to navigate a world of apples falling from trees, not Planck-scale chaos. Yet with math and imagination, we're peeling back layers of reality to reveal a universe far stranger, far more dynamic than our senses could ever grasp. And if spacetime itself is a bubbling quantum soup, what other illusions might we be taking for granted? The answer could rewrite not just physics, but the very nature of existence. Loop quantum gravity dares to ask a radical question. What if space itself isn't smooth and continuous, but stitched together from tiny, indivisible threads? Picture the universe not as an endless void, but as an intricate tapestry woven from microscopic loops, each one a fundamental atom of spacetime, vibrating with quantum energy. This theory, a bold rival to string theory, tosses out the idea of infinitely divisible space, proposing instead that reality has a granular structure at the smallest scales, like pixels on a screen. While string theory imagines particles as vibrating strings in higher dimensions, loop quantum gravity keeps things closer to home. suggesting that space itself is a dynamic network of interconnected loops, constantly evolving as gravity dances across their connections. The implications are staggering. If space is discrete, then the Big Bang wasn't the birth of reality from a singularity, a point of infinite density, but a rebound from a previous universe's collapse. Think of it like a cosmic game of elastic snapback. As the loops of spacetime compress to their limit, they reach a point of maximum tension and then spring outward, creating the expanding universe we see today. This big bounce scenario sidesteps the need for a singularity, offering a cleaner solution to the origin of everything. Suddenly, the Big Bang isn't a beginning, but a transition, a turning point in an eternal cycle of contraction and expansion. But what about black holes, those cosmic monsters where spacetime bends to its breaking point? Here, loop quantum gravity offers a tantalizing twist. Instead of a singularity at the core where general relativity predicts infinite curvature, the theory suggests that the loops of spacetime resist infinite compression, forming a dense but finite quantum star at the center. This could mean black holes aren't bottomless pits, but gateways to new physics, where the fabric of reality reorganizes itself into something stranger. Hawking radiation, the faint glow predicted to leak from black holes, might carry subtle imprints of this looped structure, like shadows cast by the underlying quantum geometry. Critics argue that loop quantum gravity lacks the experimental support of more mainstream theories, and its mathematical complexity makes it notoriously difficult to test. Yet its elegance lies in its simplicity. No extra dimensions, no unseen universes, just spacetime revealed as a shimmering web of energy, where even the void hums with quantum connections. Whether it's the final word on quantum gravity or just another step toward deeper understanding, one thing's certain: the universe is far more textured, far more intricate than we ever imagined. And if spacetime really is woven from loops, then every black hole, every galaxy, every fleeting moment is just a stitch in the grand cosmic tapestry. Stephen Hawking's most revolutionary idea wasn't about how black holes devour everything, it was about how they let go. In 1974, the physicist made a startling prediction: black holes shouldn't be perfectly black. They must emit radiation, slowly leaking energy until they vanish entirely. This Hawking radiation upended decades of astrophysics, revealing that even the universe's most voracious predators have an expiration date. The mechanism hinges on quantum weirdness near the event horizon. According to quantum theory, empty space isn't truly empty. It's a seething froth of virtual particle pairs popping in and out of existence. Normally, these particles annihilate each other instantly, but at the edge of a black hole, something bizarre happens. If one particle falls in while its partner escapes, the black hole effectively loses mass, paying the energy cost for the escaped particle's existence. Over unimaginable eons, this quantum tax adds up. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate, a number so large it dwarfs the current age of the universe. But for smaller primordial black holes formed in the chaos of the Big Bang, the process could be nearing its end right now, potentially unleashing final bursts of gamma rays as they wink out of existence. This leads to the infamous black hole information paradox. Quantum mechanics states that information, the detailed state of every particle that fell into the black hole, can never be truly destroyed. But if the black hole evaporates into random thermal radiation, where does that information go? Hawking initially argued it was lost forever, violating quantum theory's core principles. The scientific community recoiled. If correct, this would mean rewriting quantum mechanics or accepting that the universe forgets. Enter the holographic principle, a radical solution proposing that information isn't lost, it's encoded on the black hole's event horizon like a cosmic hard drive. Just as a hologram stores a three-dimensional image on a two-dimensional surface, the horizon could preserve the data of everything that fell inside. As the black hole emits Hawking radiation, this information gets imprinted onto the escaping particles, scrambled but recoverable in principle. It's as if the universe keeps receipts, ensuring no quantum debt goes unpaid. Recent breakthroughs lend credence to this wild idea. In 2019, physicists calculated that Hawking radiation does carry subtle correlations, fingerprints of the original infalling matter. Meanwhile, experiments with quantum computers simulate how information might escape evaporating black holes, revealing unexpected connections to error-correcting codes used in everyday technology. The deeper we probe, the clearer it becomes. Black holes aren't cosmic shredders but transformers, altering information in ways we're only beginning to decipher. Yet mysteries remain. Does the holographic principle apply to the entire universe, suggesting our three-dimensional reality is a projection from some distant two-dimensional boundary? And what happens in the final moments of evaporation when quantum gravity dominates? Hawking radiation isn't just about dying black holes, it's a gateway to understanding how space, time, and information weave together at the deepest levels. Every photon escaping a black hole carries not just energy, but clues to the universe's most guarded secrets. The holographic principle turns reality inside out, literally. What if everything we see, touch, and experience in three dimensions is nothing more than a shadow, a shimmering projection from information encoded on a distant, two-dimensional surface? This isn't science fiction. It's a serious theory born from the most perplexing quirks of black holes and string theory. The story begins with an unsettling discovery. When matter falls into a black hole, the information describing it doesn't vanish. Instead, it gets smeared across the event horizon like ink on a balloon, preserved in ever tinier pixels as the black hole's surface area grows. But here's the twist: the total information content doesn't depend on the volume inside the black hole, only on the area of its boundary. This revelation led physicist Gerard T. Hooft to a radical idea in the 1990s. What if the entire universe operates the same way? Just as a hologram stores a three-dimensional image on a flat surface, perhaps all the stars, galaxies, and even our own thoughts are encoded on some vast cosmic boundary we can't perceive. String theorists like Leonard Susskind ran with this, showing how the mathematics of higher dimensional spaces could indeed be rewritten as theories living on their lower dimensional edges. It's as if the universe is a grand illusion, with all the richness of 3D reality emerging from a 2D code we're only beginning to crack. But how could this possibly work? Think of it like watching a movie. The screen is flat, yet the images appear to have depth, motion, even emotion. The holographic principle suggests reality plays a similar trick, with quantum pixels on the universe's outer shell generating the depth we perceive. Even stranger, this might explain why spacetime seems smooth at large scales, but grainy up close, just as a digital image blurs into coherence when you step back from its individual pixels. The implications are staggering. If the holographic principle holds, then black holes aren't just cosmic oddities, they're Rosetta Stones, revealing the universe's true nature. It would mean the Big Bang wasn't the birth of space and time, but the unfurling of a holographic projection. Some physicists, like Nobel laureate David Gross, even speculate this could lead to a theory of everything, unifying quantum mechanics and gravity by showing how spacetime itself emerges from quantum entanglement. Yet the most mind-bending possibility is this: if the universe is a hologram, who or what is the projector? While most scientists reject outright simulation theories, the holographic principle blurs the line between physics and philosophy. Are we living in a cosmic computation, our perceptions rendered by some unfathomable algorithm? Or is nature simply more economical than we imagined, building reality from the thinnest possible brushstrokes? The answer, whatever it is, would rewrite not just physics, but our very sense of what it means to exist. And if the universe is indeed a hologram, the greatest mysteries might not lie in the stars, but in the unseen code humming just beneath the surface of reality. What if everything you've ever known, the feel of sunlight on your skin, the sound of laughter, even the stars stretching endlessly overhead, wasn't real? Not in the way we assume, at least. The simulation hypothesis suggests our universe might be an elaborate digital construct, a cosmic video game run by some advanced civilization. It sounds like the plot of a sci-fi movie, but this idea has gained startling traction among philosophers, physicists, and even Silicon Valley billionaires. At its core lies a provocative question. If future civilizations could create simulations indistinguishable from reality, wouldn't the odds favor us being inside one? The argument hinges on probability. Think of it like this. Imagine a civilization 1,000,000 years more advanced than ours. Their computing power would make ours look like abacus beads. If they chose to run ancestor simulations recreating their past with perfect detail, the number of simulated beings would vastly outnumber real ones. Statistically speaking, you're more likely to be one of those simulations than an organic original. This trilemma, formulated by philosopher Nick Bostrom, suggests at least one of three things must be true. Civilizations always go extinct before reaching simulation capability. They lose interest in creating simulations, or we're almost certainly living in one. But where's the evidence? Some point to quantum mechanics as potential glitches in the matrix. Take the observer effect, where particles exist in multiple states until measured, like a video game rendering graphics only when you look. Others note how the universe appears pixelated at the smallest scales, with Planck lengths and discrete energy levels resembling code constraints. Even mathematical universe theories, which propose reality is fundamentally made of numbers, align eerily with the idea of a computational substrate. Elon Musk famously quipped that the odds we're in base reality are 1 in billions, yet skeptics counter with physics' own built-in firewall. Simulating every particle in the universe would require unfathomable energy, far more than the universe contains. Unless, of course, the simulation cheats by rendering only what's observed, like a video game loading distant terrain as you approach. This limited rendering theory might explain why we find hard limits when probing reality's fabric. But it also raises unsettling questions. If we're in a simulation who's the programmer, some speculate it's our descendants running historical recreations. Others imagine alien superintelligences, so advanced their motives are incomprehensible. The most chilling possibility, we might never know. A sufficiently advanced simulation could prevent its inhabitants from discovering the truth, like characters in a game unaware their code. Or perhaps the answer lies in testing the universe itself, searching for anomalies in cosmic rays or quantum behavior that betray underlying computation. Either way, the simulation hypothesis forces us to confront the nature of reality itself. Whether we're stardust or strings of data, one thing's certain: the universe is far stranger than it seems. And if we are living in someone else's simulation, the real question isn't about our creators, it's about what happens when we start building simulations of our own. Imagine a civilization so advanced it doesn't just harness the energy of its home planet. It captures the entire output of its star, wrapping it in a colossal megastructure to fuel interstellar ambitions. This isn't science fiction. It's a Type 2 civilization on the Kardashev Scale, a framework dreamed up by Soviet astronomer Nikolai Kardashev in 1964 to categorize extraterrestrial societies by their energy mastery. The scale is deceptively simple. Type 1 controls all planetary resources, Type 2 commands stellar power, and Type 3 governs galaxies. But here's the humbling truth: humanity doesn't even rank a full Type 1. We're lingering around Type 0.7, still tethered to fossil fuels while squabbling over patches of dirt. The gap between where we are and where we could be is staggering. A true Type 1 civilization would harness every watt of sunlight striking Earth, tap geothermal vents, and control weather systems, rendering energy scarcity obsolete. Type 2 civilizations, like the hypothetical builders of Dyson spheres, would dismantle planets to construct star-encircling power grids, and Type 3. They'd be galaxy gardeners, bending supermassive black holes to their will or exploiting dark energy itself. The scale isn't just about bragging rights, it's a roadmap for survival. Any species that avoids self-destruction long enough to reach Type 1 status likely secures its future against planetary disasters, asteroids, ice ages, even dying suns. Yet the scale also highlights the eerie silence of the cosmos. If advanced civilizations are inevitable, where are they? This is Fermi's paradox in a nutshell. The universe is ancient and vast, with billions of potentially habitable planets, so statistically, someone should have colonized the Milky Way by now. The fact that we haven't found so much as a radio whisper suggests something's amiss. Maybe civilizations inevitably annihilate themselves before reaching Type 1, a sobering thought as we flirt with nuclear war and climate collapse. Or perhaps they transcend physical form, uploading consciousness into quantum clouds, leaving no trace for primitive species like us to detect. There's a darker twist. What if advanced civilizations aren't hiding but deliberately avoiding us? The zoo hypothesis posits that Earth might be a protected reserve, with galactic neighbors observing us like animals in a cosmic safari park until we mature enough to join the interstellar community. Alternatively, the distances might simply be too vast. Even a Type 3 civilization would take millennia to traverse a galaxy, making contact unlikely without wormholes or warp drives. The Kardashev scale doesn't just measure energy, it measures potential. Every watt we harness, every solar panel we deploy, nudges us closer to Type 1. But the scale also asks uncomfortable questions. Are we alone because intelligence is vanishingly rare, or because the universe is littered with the ruins of civilizations that failed the test? The answer might determine whether humanity's future lies among the stars or ends as a cautionary footnote in cosmic history. One thing's certain: the scale reminds us that intelligence alone isn't enough. Survival requires wisdom, the kind that turns energy into enlightenment, not ashes. And if we ever do detect a signal from a Type 2 civilization, it won't just answer whether we're alone. It'll tell us whether we're doomed or just getting started. The universe is ancient beyond comprehension, 13.8 billion years old, with 2 trillion galaxies, each hosting billions of stars. Statistically, life should have emerged countless times, flourishing into civilizations capable of painting their presence across the cosmos. Yet when we listen, the universe echoes with silence. This is the Fermi Paradox, the glaring contradiction between the high probability of extraterrestrial life and the utter lack of evidence for it. If the universe is so vast and old, where is everybody? One chilling answer is the dark forest theory, inspired by the eerie quiet of an unexplored woodland. Imagine every civilization as a hunter hiding in the cosmic trees, terrified of revealing their location. In this scenario, advanced societies don't broadcast their existence, they stay silent, because any signal could attract predators or competitors far more powerful. The first rule of the dark forest is simple: never light a fire. This might explain why SETI radio telescopes hear nothing, not because space is empty, but because every intelligent species has learned the same brutal lesson: visibility is suicide. Then there's the zoo hypothesis, a gentler but equally unsettling idea. What if Earth is a protected planet, deliberately quarantined by a galactic community, waiting for us to reach some evolutionary milestone? Like anthropologists observing an uncontacted tribe, they might avoid interference to preserve our natural development. The irony is crushing. We scour the skies for neighbors who could be watching us, choosing not to speak until we're mature enough to handle the truth. But not all hope is lost. In 1977, Ohio's Big Ear radio telescope picked up the infamous WOW signal, a 72-second burst of radiation so precisely tuned to the hydrogen line frequency that it seemed engineered for interstellar communication. The signal vanished as suddenly as it appeared, never repeating despite decades of follow-up searches. Was it a cosmic flare, a glitch, or a fleeting hello from a civilization that blinked out millennia ago? The mystery endures, a tantalizing maybe in a universe full of silence. The paradox forces us to confront uncomfortable possibilities. Maybe civilizations inevitably destroy themselves before achieving interstellar travel, a sobering thought as we grapple with nuclear arsenals and climate crises. Or perhaps intelligence is rarer than we think, with Earth as a freak accident in an otherwise sterile cosmos. There's another, darker twist. What if we're simply too primitive to recognize the signs? Advanced civilizations might communicate via neutrino beams or quantum entanglement, technologies as incomprehensible to us as radio waves would be to ants. The silence isn't just a puzzle, it's a mirror. Every hypothesis reflects our own fears and hopes back at us. Are we alone because the universe is a battlefield, a sanctuary, or a graveyard? The answer, if it ever comes, won't just tell us about aliens. It'll reveal whether humanity's future lies among the stars or ends as a whisper in an indifferent cosmos. And until then, the stars keep their secrets, leaving us to wonder if the greatest mystery isn't out there at all, but within us. On August 15, 1977, a radio telescope at Ohio State University's Big Ear Observatory picked up something extraordinary, a signal so strong, so perfectly tuned to the frequency of interstellar hydrogen, that astronomer Jerry Amon circled it in red pen and scribbled, "Wow." Next to the data, that single word would immortalize the most tantalizing blip in the history of the search for extraterrestrial intelligence. For 72 seconds, the signal blared at 30 times the background noise, matching the exact wavelength that scientists had theorized aliens might use to announce their presence. Then, just as suddenly as it appeared, it vanished, never to be heard again, despite decades of relentless searching. What made the WOW signal so electrifying wasn't just its intensity, but its precision. It hit 1,420 megahertz, a quiet frequency where cosmic noise is minimal, like shouting in an empty canyon. Natural phenomena like pulsars or comets couldn't explain it. They don't transmit such narrow, focused bursts. Even more intriguing, the signal's strength rose and fell in a curve perfectly matching Earth's rotation, as if it were a beacon fixed in space, briefly spotlighted by the telescope's gaze. It felt deliberate, designed, yet after scanning the same patch of sky in the constellation Sagittarius over and over, astronomers found only silence. Theories abound. Some argue it was a passing satellite or a military transmission, though no known technology at the time matched the signal's profile. Others suggest a rogue celestial object like a comet, reflecting sunlight in just the right way, except comets don't emit radio waves at that frequency. Then there's the haunting possibility that it was indeed a message, but one we missed by mere cosmic seconds. Imagine another civilization pointing a transmitter our way, sending a pulse that swept past Earth like a lighthouse beam, never to return. Fast forward to today, and the mystery deepens with the discovery of fast radio bursts, ultra-powerful, millisecond-long blasts of energy from distant galaxies. Like the WOW signal, these bursts are transient and unpredictable, but they originate billions of light years away, ruling out local interference. Some repeat in patterns, others vanish forever. While most are likely caused by magnetars or colliding neutron stars, a handful defy explanation, sparking speculation about artificial origins. Could the WOW signal have been an early, nearby example of this phenomenon, or was it something else entirely? The silence since then might be the most telling clue. If advanced civilizations exist, why wouldn't they broadcast continuously? One unsettling answer lies in the dark forest hypothesis, the idea that intelligent species stay hidden to avoid attracting hostile attention. In this cosmic game of hide and seek, a single hello could be catastrophic. Alternatively, we might be listening for the wrong thing. Alien communication could use neutrino beams or quantum entanglement, technologies as alien to us as radio waves would be to Stone Age hunters. The WOW signal endures as both a beacon of hope and a cautionary tale. It reminds us that the universe is vast enough to hold unimaginable wonders and humbling enough to keep them just out of reach. Whether it was a cosmic fluke or a greeting lost to time, one thing's certain: the stars have more secrets than we've dared to dream, and the next signal, if it ever comes, might not just answer whether we're alone, it could rewrite everything we think we know. Fast radio bursts are the universe's most enigmatic Morse code, blinding flashes of energy that vanish in milliseconds, yet pack more power than the sun emits in days. First detected in 2007, these cosmic bursts originate billions of light years away, some from galaxies so distant their light has traveled half the age of the universe to reach us. What makes them truly baffling is their unpredictability. Most burst once and disappear forever like cosmic firecrackers, but a handful like FRB 1211 in the constellation Auriga repeat sporadically, flickering on and off with no discernible pattern. It's as if the cosmos is teasing us with a riddle it refuses to solve. The leading suspect, magnetars neutron stars with magnetic fields so intense they could rip atoms apart from halfway across the solar system. When these stellar zombies undergo starquakes, their crusts crack under magnetic strain, potentially releasing torrents of energy as fast radio bursts. Supporting this, astronomers in 2020 linked an FRB to a magnetar in our own galaxy, the first smoking gun connecting these bursts to a known object. Yet mysteries remain. Most extragalactic FRBs are far more energetic than their galactic cousins, suggesting something even more violent might lurk behind them. Could colliding neutron stars or evaporating black holes be the culprits? Or is the truth something no one has dared to imagine? This is where things get speculative. In 2017, Harvard astronomers Shostak and Loeb raised eyebrows by suggesting some repeating bursts might be artificial leakage from alien light sails harnessing cosmic radiation to propel spacecraft. The idea isn't entirely far-fetched. A civilization advanced enough to build planet-sized transmitters could theoretically blast focused energy beams across intergalactic distances, with FRBs as accidental byproducts. The math holds up. To accelerate a massive starship to near light speed would require beams matching the power and duration of observed FRBs. enter Oumuamua, the interstellar visitor that whipped through our solar system in 2017. Its bizarre acceleration, unexplained by gravity alone, led some to ponder whether it might be artificial, a notion Loeb famously championed. While most scientists attribute its behavior to outgassing hydrogen, the coincidence is striking. Just as we grapple with unexplained cosmic signals, an unidentifiable object streaks past, defying expectations. It's a reminder that the universe has a habit of humbling our assumptions. The truth likely lies between the mundane and the extraordinary. FRBs could be natural phenomena we've yet to discover. Perhaps cosmic lightning from collapsing wormholes or vibrations in the fabric of space-time itself. But their very existence proves how much we still don't understand about the high-energy universe. Every new burst is a cipher, a fleeting clue whispered across billions of years. And whether their sources are magnetars, aliens, or something beyond our current physics, one thing's certain: the cosmos is far stranger and far more inventive than we've dared to dream. Oumuamua wasn't just another space rock, it was a cosmic mystery wrapped in an enigma, tumbling through our solar system like a guest who crashes the party and leaves before anyone can ask questions. When astronomers first spotted it in October 2017, this bizarre, cigar-shaped object was already speeding away, having swung around the sun at blistering speeds. Its trajectory was unmistakable. Oumuamua didn't belong here. It was the first confirmed visitor from another star system, a wanderer from realms beyond our sun's reach. But what made it truly extraordinary wasn't just its origin. It was the way it moved. Instead of slowing down as expected after its solar close encounter, Oumuamua accelerated, as if pushed by some unseen force. At first, scientists scrambled for conventional explanations. Maybe it was a comet venting gas that acted like a natural thruster, but there was no visible coma, no telltale haze of evaporating ice. Others suggested it might be a rare type of asteroid, a shard of a shattered planet ejected into interstellar space. Yet none of these fully accounted for its odd acceleration. Then came the bombshell hypothesis from Harvard astrophysicist Avi Loeb. What if Oumuamua wasn't natural at all? Could it be a piece of alien technology, a discarded light sail perhaps, or a derelict probe? The idea sent shockwaves through the scientific community. Critics dismissed it as sensationalism, but Loeb pointed to the object's peculiar shape, unusually elongated, like a pancake, and its reflectivity, which suggested a metallic surface. If Oumuamua was artificial, it might explain why it defied gravity's rules, but here's where the plot thickens. Even if Oumuamua was natural, its very existence hints at a universe teeming with interstellar travelers. Current models suggest our solar system should harbor thousands of such objects at any given time, most too faint to detect. Some might even be dark comets, icy bodies cloaked in organic material, invisible until they flare up unexpectedly. In 2020, astronomers spotted another likely interstellar visitor, Comet Borisov, which behaved far more predictably. Unlike Oumuamua, Borisov sported a classic cometary tail, proving that not all interstellar objects are weird. But the fact that two such visitors appeared within years of each other suggests the cosmos is bustling with hidden nomads, each carrying secrets from distant stars. What's thrilling is how little we know. Future telescopes like the Vera Rubin Observatory, set to scan the entire southern sky every few nights, promise to catch more of these fleeting guests. Each one could be a Rosetta Stone, offering clues about how planetary systems form, or just maybe evidence that we're not the only ones curious about the universe. Whether Oumuamua was a strange quirk of nature or something more, it's a reminder that the cosmos still has surprises up its sleeve, and the next visitor might not just pass through, it could stop to say hello. Dark comets are the universe's stealthy infiltrators, cosmic icebergs cloaked in shadows, slipping through the solar system without the fanfare of glowing tails or shimmering comas. Unlike their more flamboyant cousins, these enigmatic wanderers don't announce their presence with streaks of vaporized ice. Instead, they're wrapped in layers of dark organic material, absorbing sunlight rather than reflecting it, making them nearly invisible until they're practically on our doorstep. Take Comet-era's Arachialcock, which in 1983 whizzed past Earth at a mere 5 million kilometers closer than any known comet in 2 centuries, yet was detected only weeks before its approach. Its muted appearance fooled telescopes, a chilling reminder of how vulnerable we might be to these camouflaged intruders. What makes dark comets so elusive? The answer lies in their chemistry. Ordinary comets like Halley or Hale-Bopp are cosmic snowballs, mixtures of ice, dust, and rock that heat up as they near the sun, shedding dazzling tails of gas and debris. Dark comets, by contrast, are more like tar-covered snowballs. Their surfaces are rich in complex organic compounds, think asphalt-like substances, that absorb heat without easily vaporizing. This means they don't produce the telltale glow of sublimating ice, rendering them virtually invisible to surveys that hunt for the reflective signatures of typical comets. Some might even be burnt-out comets, their volatile ices long exhausted after countless orbits, leaving behind inert, asteroid-like husks that still pack the mass and momentum to cause planetary devastation. The threat isn't theoretical. In 2017, asteroid 2017-001 slipped past Earth at just a third of the lunar distance undetected until days after its closest approach. Later analysis suggested it might actually be a dark comet, its lack of outgassing fooling our detection systems. This near miss underscores a gaping hole in planetary defense, our reliance on sunlight-reflecting surveys. Current telescopes like Pan-STARRS or the upcoming Vera Rubin Observatory excel at spotting shiny objects, but dark comets could evade them until it's too late. The consequences of a direct hit are stomach-churning. A dark comet just 200 meters wide could unleash energy equivalent to thousands of Hiroshima bombs, flattening entire regions and altering global climate. Yet there's hope on the horizon. New infrared telescopes like NASA and NEO-Surveyor aim to catch these stealthy threats by sensing their heat signatures rather than reflected light. Meanwhile, missions like ESA's Comet Interceptor are designed to rendezvous with incoming objects, potentially revealing the secrets of their dark surfaces. The stakes couldn't be higher. Understanding dark comets isn't just about cataloging curiosities, it's about rewriting the playbook for planetary survival. And as we sharpen our tools to spot these cosmic phantoms, we're forced to confront a humbling truth. The universe doesn't just hide its wonders in plain sight. Sometimes the greatest dangers are the ones we can't see. But while dark comets slink through the shadows, another cosmic phenomenon barrels toward us with unnerving regularity near Earth asteroids, some of which have come alarmingly close to rewriting human history. The next chapter in our cosmic defense saga reveals just how narrow our escapes have been. On the morning of June 30th, 1908, a fireball streaked across the skies of Siberia with the brilliance of a second sun. Moments later, an explosion ripped through the air near the Podkamennaya Tunguska River with a force of 10 to 15 megatons, nearly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The blast flattened 80 million trees across 2,000 square kilometers, toppling them in a radial pattern like matchsticks. Eyewitnesses dozens of kilometers away described searing heat waves, deafening shockwaves, and towering mushroom clouds. Yet when scientists finally reached the remote site 19 years later, they found no crater, no fragments of a meteorite, just a silent, scorched forest frozen in time. This was the Tunguska event, one of the most violent cosmic encounters in recorded history. The leading theory, a stony asteroid or icy comet fragment, roughly 60 meters wide, entered Earth's atmosphere at 54,000 kilometers per hour. Unlike most space rocks that impact the ground, this one likely disintegrated 5 to 10 kilometers above the surface, its kinetic energy converting instantly into a superheated shockwave. The absence of a crater suggests it wasn't the ground that took the hit, it was the air itself, compressed so violently it became a weapon of mass destruction. Trees directly below the blast were stripped bare, their branches vaporized, while those farther out were knocked flat in a symmetrical pattern. If the explosion had occurred over a major city, the death toll could have reached millions. What makes Tunguska so unnerving isn't just its scale, it's how recently it happened. A century is a blink in cosmic terms, and Earth's close calls haven't stopped. In 2013, the Chelyabinsk meteor reminded us of our vulnerability when a 20-meter asteroid detonated over Russia with half a megaton of force. The blast shattered windows across 6 cities, injuring over 1,500 people, mostly from flying glass. Unlike Tunguska, this event was captured on countless dashcams, offering a chilling real-time glimpse of what a larger impact might look like. The Chelyabinsk rock arrived without warning, hidden by the sun's glare, proving that even in our age of technology, the cosmos can still catch us off guard. Statistically, Tunguska scale events occur every few centuries, while smaller impacts like Chelyabinsk happen every few decades. NASA estimates there are over 25,000 near-Earth asteroids larger than 140 meters, big enough to devastate continents, and we've catalogued less than half. Comets, which can approach from any direction at higher speeds, are even harder to track. The irony is stark. We live on a planet perpetually orbiting through a cosmic shooting gallery, yet most people remain oblivious to the danger. The lesson of Tunguska isn't fear, it's preparation. Initiatives like the double asteroid redirection test, which successfully nudged a harmless asteroid off course in 2022, prove we're not powerless. Early warning telescopes like the upcoming NEO Surveyor space mission aim to spot threats years in advance, but the real challenge isn't technical, it's political. Deflecting an asteroid requires global cooperation and funding a hard sell when the threat feels abstract. Tunguska and Chelyabinsk are wake-up calls written in fire across the sky. Planetary defense isn't science fiction. It's survival, and the next cosmic bullet might not miss. Yet for all their destructive potential, these events also remind us of our cosmic connection. The same asteroids that threaten extinction also delivered the water and organic molecules that made life possible. They're both destroyers and creators, woven into the story of our planet. The question isn't whether another Tunguska will happen, it's when. And when it does, will we be watching the skies or will we be caught looking the other way? Chelyabinsk wasn't supposed to happen, not in the 21st century, not with our eyes supposedly scanning the skies. Yet on February 15, 2013, a 20-meter asteroid, undetected and uninvited, sliced through the atmosphere over Russia at 60,000 kilometers per hour. The fireball burned 30 times brighter than the sun, its shockwave shattering windows across 6 cities, injuring over 1,500 people. Security cameras captured the moment the morning commute turned surreal commuters thrown to the ground by the blast wave, car alarms wailing as the sky flashed white. The explosion released energy equivalent to 30 Hiroshima bombs, all from a space rock no bigger than a school bus. What made Chelyabinsk so jarring wasn't its size, it was our blindness to it. The asteroid approached from the sun's direction, hidden in the glare where telescopes couldn't see it. unlike Hollywood's doomsday scenarios, there were no heroic last-minute deflections, no global panic. Just ordinary people going about their day when the universe reminded us how fragile our sense of security really is. In the aftermath, scientists combed through debris and dashcam footage, piecing together clues. This wasn't some metallic menace. It was a stony asteroid, the kind that vaporizes violently in the atmosphere. Had it entered at a steeper angle, the damage could have been catastrophic. The event sparked more than broken glass, it shattered complacency. Within months, NASA accelerated efforts to track near-Earth objects, doubling down on projects like Atlas, a telescope network designed to spot asteroids days, not hours, before impact. The data revealed an uncomfortable truth. We'd catalogued less than 1% of potentially hazardous objects under 30 meters, the size most likely to slip through our defenses yet still pack a punch. But detection is only half the battle. The real question is, if we spot the next Chelyabinsk or something larger, can we stop it? Enter a DART mission, a cosmic game of billiards played at 15,000 kilometers per hour. In 2022, the spacecraft intentionally crashed into Dimorphos, a harmless moonlet orbiting the asteroid Didymos. The goal wasn't destruction, it was deflection. By altering Dimorphos's orbit by 32 minutes, DART proved humanity could, in theory, nudge an asteroid off a collision course given enough lead time. Yet challenges loom. Dimorphos was a straightforward target, small, slow-moving, and conveniently paired. A real threat might be tumbling unpredictably or made of loosely packed rubble that absorbs impacts like a cosmic sponge. Alternative ideas abound. Gravity tractors that slowly tow asteroids using their own mass, or nuclear devices detonated nearby to vaporize surface material and create thrust. Each method has trade-offs, and none are battle-tested against an actual doomsday rock. Chelyabinsk was a warning shot, a reminder that the universe doesn't operate on human timelines. The next impact might not just break windows, it could rewrite history, but for the first time, we're not just potential victims. We're students of the cosmos, learning to read its patterns and perhaps sway its course. The question isn't whether another asteroid will come, it's whether we'll be ready when it does. And if the answer is yes, it'll be because we heeded the lessons written in the skies over Russia that winter morning. The DART mission wasn't just a scientific experiment, it was humanity's first real attempt to play cosmic billiards with an asteroid, and the stakes couldn't have been higher. In September 2022, NASA refrigerator-sized spacecraft hurtled toward Dimorphos, a harmless moonlet orbiting the asteroid Didymos, and slammed into it at over 22,000 kilometers per hour. The goal wasn't destruction, it was deflection. For the first time in history, we weren't just watching the skies for threats, we were actively testing how to change their course. The results were staggering. The impact altered Dimorphos's orbit by 32 minutes, proving that even a modest nudge could, given enough time, steer a dangerous asteroid away from Earth. But how does knocking a space rock off its path actually work? It's all about momentum. Think of a slow-moving bowling ball hitting a stationary pin. The pin doesn't shatter. It rolls away, its trajectory subtly shifted. DART operated on the same principle, transferring its kinetic energy to Dimorphos in a controlled collision. What surprised scientists wasn't just the orbital change, but the aftermath. The impact ejected a plume of debris, creating a natural thruster effect that amplified the deflection. This ejector momentum enhancement means future missions might need less force than expected to achieve the same result, a revelation that could reshape planetary defense strategies. Now the big question, if we can deflect asteroids, should we also mine them? The economics are jaw-dropping. A single metallic asteroid like 16 Psyche contains enough iron, nickel, and precious metals to dwarf Earth's entire mining output. Platinum group metals, rare on our planet, abound in these floating treasure chests. Companies like Planetary Resources and Deep Space Industries have already drawn up blueprints for robotic miners that could extract water for fuel or metals for construction in space. The challenge isn't just technical, it's legal. The Outer Space Treaty of 1967 forbids nations from claiming celestial bodies, but says nothing about corporations harvesting resources. This gray zone has sparked a gold rush mentality, with Luxembourg and the US passing laws to encourage commercial asteroid mining, yet the risks are as vast as the rewards. Mining could destabilize an asteroid's structure, inadvertently sending fragments spiraling toward Earth. Others argue that tampering with near-Earth objects might violate an unspoken cosmic prime directive. Don't mess with what you don't understand. After all, these rocks have orbited peacefully for eons. Could our hunger for resources turn them into unintended threats? The DART mission proved we're no longer passive observers of the cosmos. We're becoming gardeners of the solar system, capable of pruning hazards and cultivating opportunities. But with that power comes a responsibility to wield it wisely, because the line between defense and disruption is thinner than we think. And as we reach for the asteroids, we're not just grabbing rocks, we're grabbing hold of our future. Asteroids aren't just cosmic debris, they're floating vaults stuffed with riches beyond imagination. Picture a single metallic space rock like 16 Psyche, drifting between Mars and Jupiter. Scientists estimate its iron and nickel alone could be worth $10,000 quadrillion at current market prices, enough to give every person on Earth over $1 billion. But it's not just about wealth. These celestial bodies hold something even more valuable for space exploration: water. Frozen in the shadows of carbonaceous asteroids, water can be split into hydrogen and oxygen, the very fuels that power rockets. Suddenly, asteroids aren't just targets for miners. They're interplanetary gas stations fueling humanity's leap deeper into the cosmos. The technology to make this sci-fi vision real is already taking shape. Companies like Astroforge and TransAstra are testing compact refineries that could hitch rides on spacecraft, using solar heat to vaporize asteroid material and separate metals from slag. Meanwhile, NASA OSIRIS-REx mission proved we can land on asteroids and scoop up samples returning to Earth with a cache of pristine space rock in 2023. The next step: robots. Imagine autonomous drones equipped with drills and spectrometers, mapping resource-rich asteroids like cosmic surveyors before deploying modular processing plants. These wouldn't be the clunky machines of today, but nimble, AI-driven prospectors capable of operating in zero gravity with pinpoint precision. But here's where things get messy. Who owns the right to mine these celestial bodies? The 1967 Outer Space Treaty bans nations from claiming sovereignty over asteroids or moons, but it's silent on corporations extracting resources. In 2015, the U.S. passed the Commercial Space Launch Competitiveness Act, granting American companies rights to whatever they mine in space, a move likened to the Wild West land rushes. Luxembourg followed suit, offering tax incentives for space mining ventures. Critics argue this creates a legal gray zone where wealthy nations and corporations could de facto control off-world resources, leaving developing countries earthbound. The ethical dilemmas run deeper. Should we treat asteroids as infinite commodities, or would reckless mining risk altering their orbits, inadvertently creating new threats for Earth? Some scientists propose designating certain asteroids as protected scientific reserves, their pristine compositions holding clues to the solar system's origins. Others worry a gold rush mentality could trigger conflicts. Imagine rival companies sabotaging each other's operations millions of miles from law enforcement. Yet the potential rewards are too staggering to ignore. Asteroid-derived platinum could revolutionize clean energy by making hydrogen fuel cells affordable worldwide. Silicon from space rocks might build solar panels in orbit, beaming limitless energy back to Earth. And every ton of water mined off-planet saves the $20,000 cost of launching it from Earth's gravity well. This isn't just about profit, it's about sustainability, reducing our reliance on terrestrial mining's environmental toll while enabling permanent lunar bases and Mars colonies. The path forward demands balance. International agreements like the Artemis Accords are starting to frame how nations share space resources, but enforcement remains spotty. Perhaps the model isn't Earth's contentious history of colonization, but Antarctica's cooperative research ethos, a frontier managed for collective benefit. One thing's certain, as we reach for these cosmic treasures, we're not just mining rocks, we're shaping the rules of our multi-planet future, and the choices we make today will echo across the solar system for generations to come. Space law might sound like the premise of a sci-fi novel, but it's one of the most urgent and underrated challenges of our era. The current legal framework hinges on the 1967 Outer Space Treaty, a Cold War-era document signed when only 2 nations had reached orbit. Its core principles seem noble: space is the province of all mankind. Celestial bodies can't be claimed by nations, and weapons of mass destruction are banned beyond Earth. But today, as private companies drill for lunar ice and nations jockey for Martian real estate, this treaty is showing its age. Consider the Artemis Accords, a 21st-century addendum spearheaded by NASA, which allows safety zones around lunar operations. Critics argue these zones could become de facto territory grabs, exploiting loopholes in the original treaty's vague language. Meanwhile, countries like China and Russia are drafting their own rules, raising the specter of a fragmented, Wild West-style legal landscape in orbit. The stakes escalate when you examine who's at the table and who isn't. Only a handful of spacefaring nations shape policies today, while the majority of countries risk being left out of the cosmic gold rush. Luxembourg, a tiny European nation, has become a hub for asteroid mining ventures thanks to progressive space resource laws. Should a single corporation or nation control access to water ice in permanently shadowed lunar craters, a resource critical for future Mars missions? The treaty's ambiguity fuels these tensions, with no clear mechanism to prevent monopolies or ensure equitable distribution. Then there's the ticking time bomb of space junk. Over 28,000 tracked fragments, spent rocket stages, dead satellites, even a lost wrench now zip through orbit at speeds 10 times faster than a bullet. Each piece is a potential projectile that could trigger the Kessler Syndrome, a chain reaction of collisions rendering low Earth orbit unusable for generations. Current laws barely address this. The Liability Convention of 1972 holds nations responsible for damage caused by their spacecraft, but it's never been tested for orbital debris. When SpaceX's Starlink satellites jostled with a European Space Agency probe in 2019, no legal precedent existed to assign blame. Solutions are as complex as the problem. Some propose active debris removal, with missions like ESA's Clear Space One aiming to capture and deorbit defunct satellites. Others advocate for mandatory end-of-life plans, forcing operators to reserve fuel for safe disposal. But without binding international agreements, compliance is spotty. The real test will come when a rogue piece of debris takes out a critical satellite. Will nations collaborate or point fingers? As we stand on the brink of a multi-planet economy, space law isn't just about treaties, it's about survival. The next decade will decide whether we export Earth's conflicts to the stars or forge a new paradigm of cooperation. And if history's any guide, the rules won't be written until after the first crisis hits. The question is, will it be too late? Imagine this. A single collision between two satellites sends thousands of shards of debris hurtling through orbit at 28,000 kilometers per hour. Each fragment becomes a bullet capable of destroying other satellites, creating even more debris, triggering a chain reaction that could encase Earth in an impassable shell of shrapnel. This nightmare scenario isn't science fiction. It's the Kessler Syndrome, a real and growing threat that could cut off humanity's access to space for generations. Named after NASA scientist Donald Kessler, who first theorized it in 1978, this cascading effect could turn low Earth orbit into a cosmic minefield, where every new satellite launch becomes a gamble against escalating destruction. The math is terrifying. Currently, over 120 million pieces of debris larger than 1 millimeter orbit Earth, everything from spent rocket stages to flecks of paint. Even something as small as a screw can strike with the force of a hand grenade when traveling at orbital speeds. In 2009, a defunct Russian satellite collided with an active American one, generating over 2,000 trackable fragments. Worse still, in 2007, China's anti-satellite missile test created a debris cloud containing more than 3,000 pieces, some of which will remain in orbit for centuries. These events aren't just isolated incidents, they're previews of what could become routine if we don't intervene. So how close are we to the tipping point? Studies suggest we're already in the critical phase, where certain orbital altitudes have enough debris to make collisions inevitable without active mitigation. The European Space Agency estimates that, even if no new satellites were launched, debris levels would keep rising due to existing objects colliding. It's a sobering realization. We might be past the point where prevention alone is enough. Now, the race is on to clean up what's already there. Enter the cleanup crews of the future. Startups like Astroscale and ClearSpace are pioneering missions to capture and deorbit defunct satellites using robotic arms and magnetic docking systems. In 2021, Astroscale's ELSA-D prototype successfully demonstrated debris rendezvous technology, while ESA's ClearSpace One, slated for launch in 2026, will deploy a 4-armed robot to grapple a discarded rocket adapter and drag it into Earth's atmosphere to burn up. These missions are groundbreaking, but they're also drops in a cosmic ocean. Removing a few large objects helps, but the real challenge lies in tackling the millions of smaller, faster-moving fragments that could still trigger a cascade. That's where innovative solutions like solar sails come in. These ultra-thin, reflective sheets harness the gentle pressure of sunlight to gradually nudge debris into lower orbits, where atmospheric drag pulls them to a fiery demise. Japan's Ikaro's mission proved solar sail technology works, and projects like the Breakthrough Starshot initiative aim to push the concept further. For debris too small to track, ground-based lasers could provide another answer, firing precise beams to vaporize surface material and create thrust, steering fragments away from collisions. It sounds like something from a sci-fi arsenal, but labs are already testing prototypes. The stakes couldn't be higher. Without intervention, we risk a future where space launches become impossible, trapping humanity beneath a barrier of our own making. GPS, weather forecasting, global communications, all rely on satellites we can't afford to lose. But here's the hopeful twist. Unlike climate change or asteroid impacts, the Kessler Syndrome is entirely preventable. With international cooperation, smarter satellite design, and aggressive cleanup efforts, we can avoid this self-inflicted crisis. The question isn't whether we have the tools, it's whether we'll use them before it's too late. And as the skies grow more crowded, the clock is ticking louder than ever. Solar sails are the quiet revolutionaries of space travel. No roaring engines, no plumes of exhaust, just the gentle but relentless push of sunlight itself. Picture a spacecraft unfurling a vast, mirrored sail thinner than a human hair, catching photons from the sun like a cosmic wind. Each particle of light might be insignificant on its own, but together, their collective pressure can propel a craft forward, building speed over time without an ounce of fuel. It's a concept that sounds like science fiction, but missions like Light Sail 2 have already proven it works. Launched in 2019 by the Planetary Society, this shoebox-sized satellite deployed a 32-square-meter sail and spent months gracefully adjusting its orbit using nothing but sunlight. The implications are staggering. Spacecraft that never run out of propulsion, capable of theoretically traveling forever as long as the sun shines, but sunlight has its limits. Beyond the inner solar system, its intensity drops sharply, leaving sails starved for momentum. That's where lasers come in. Projects like Breakthrough Starshot envision firing ground-based laser arrays at tiny, sail-equipped probes, accelerating them to 20% the speed of light within minutes. At that pace, a flyby of Alpha Centauri, our nearest star system, could take just 20 years instead of millennia. The catch: the sails would need to be nearly perfect reflectors, and the lasers would require power outputs rivaling entire cities. Yet the math checks out, and early tests are already underway. In 2021, scientists successfully demonstrated laser-driven light sails in vacuum chambers, nudging microscopic sails forward with pinpoint beams. The beauty of solar sails lies in their simplicity. Unlike chemical rockets or ion drives, they have no moving parts to wear out, no fuel tanks to deplete. They could enable missions too risky or expensive for conventional propulsion, like hovering indefinitely at gravitational sweet spots to monitor solar storms or darting between asteroids with pinpoint precision. Future concepts even propose using them as interstellar garbage trucks, slowly clearing debris from Earth's orbit by nudging it into the atmosphere. And while they may never replace rockets for quick trips to Mars, they offer something far more valuable: patience. In a universe where speed often means sacrifice, solar sails remind us that sometimes the slow and steady approach unlocks journeys we never thought possible. Yet the real triumph isn't just the technology, it's the philosophy. Solar sails prove humanity can harness the universe's natural forces without brute force, turning something as ephemeral as light into an engine for exploration. Whether it's catching sunbeams or riding laser highways, these sails are more than tools. They're a testament to our ingenuity, showing that even the faintest push, given enough time, can carry us to the stars. Breaking the interstellar barrier isn't just a dream anymore, it's a blueprint. Breakthrough Starshot, the audacious brainchild of physicist Philip Lubin and backed by billionaire Yuri Milner, aims to fling a fleet of gram-scale probes toward Alpha Centauri at 20% the speed of light. That's over 134 million miles per hour, fast enough to reach our nearest stellar neighbor in just 20 years instead of the millennia it would take conventional rockets. The secret, Earth-bound lasers, collectively firing a 100-gigawatt beam at featherweight light sails attached to each probe. Picture a stadium-sized array of lasers focusing their power onto a sail no thicker than a soap bubble, accelerating these nanocraft to relativistic speeds within minutes. It's like hitting a cosmic fast-forward button, leveraging physics so elegantly simple it feels almost magical. but the challenges are as immense as the ambition. First, there's the sail material itself. It must reflect 99.999% of the laser light to avoid vaporizing under the beam's intensity. Scientists are experimenting with ultra-thin sheets of metamaterials, engineered at the atomic level to bounce photons with near-perfect efficiency. Then there's the problem of aim. Over 4 light-years, even a microscopic deviation in trajectory could send the probes hurtling past Alpha Centauri into the void. To compensate, engineers propose equipping the sails with tiny thrusters, perhaps fueled by vaporized coatings that adjust course like a spacefaring firefly. And let's not forget the lasers. Building a phased array spanning kilometers, synchronized with atomic clock precision, would demand breakthroughs in energy storage and optics we've barely begun to explore. What awaits at Alpha Centauri, the system's red dwarf star Proxima Centauri, hosts at least one tantalizing world, Proxima b, a rocky exoplanet nestled in the habitable zone where liquid water could exist. But this isn't Earth 2.0. Proxima b orbits so close to its star that it's likely tidally locked, one side perpetually scorched by flares, the other frozen in darkness. If life clings to existence there, it might huddle in the twilight zone between these extremes or thrive underground, shielded from radiation. Starshot's probes, equipped with cameras and spectrometers smaller than a postage stamp, could beam back our first close-up data of an alien world's atmosphere, geology, or even biosignatures. Imagine peering into the skies of another planet and spotting methane spikes or oxygen patterns that whisper of unseen biology. Yet the real revolution isn't just reaching another star, it's transforming how we think about exploration. Starshot's probes cost a fraction of traditional missions, making interstellar travel a swarm effort rather than a one-shot gamble. Lose a few to cosmic dust or laser misalignment. No matter, send hundreds. This isn't just about Alpha Centauri either. The same technology could dispatch probes to icy moons, distant asteroids, or interstellar objects like Oumuamua, turning the solar system into our backyard. Of course, skeptics abound. The energy demands are Herculean. The laser array would need power equivalent to a nuclear plant's output concentrated into minutes. Then there's the question of communication. How do you transmit data back to Earth across 4.37 light-years with a milliwatt laser? Proposed solutions include leveraging the sail itself as an antenna or using quantum communication tricks we've yet to invent. But here's the kicker: even if Starshot fails, it forces us to confront the cosmic hurdles head-on, proving that interstellar travel isn't a fantasy. It's an engineering puzzle waiting to be solved. So while we may not live to see Starshot's probes arrive, their legacy is already written in the questions they've ignited. What does it mean to send human ingenuity racing toward the stars at a fifth of light speed? That we refuse to be bound by the limits of our cradle, that the universe, for all its vastness, might one day feel just a little bit smaller, and who knows, perhaps the first flicker of data from Proxima b will arrive on a day when the children of today are grandparents, handing them the keys to a galaxy suddenly within reach. Proxima b isn't just another exoplanet, it's our cosmic next-door neighbor, orbiting Proxima Centauri, the closest star to our Sun at just 4.24 light-years away. Discovered in 2016, this rocky world is roughly 17% more massive than Earth, nestled snugly in its star's habitable zone where temperatures might allow liquid water to pool on its surface. But before we picture lush alien forests, let's talk about the harsh realities of this tantalizing world. Proxima Centauri is a red dwarf, a type of star notorious for its violent mood swings. Unlike our steady sun, this star unleashes frequent, devastating flares, outbursts of radiation so intense they could strip away atmospheres, and bathe any surface life in lethal doses of ultraviolet light. In 2019, one such flare briefly made Proxima Centauri 10,000 times brighter, a stellar tantrum that would have fried any nearby planets. Yet life, as we've learned on Earth, is stubborn. If Proxima b has a robust magnetic field, it might shield its atmosphere from erosion. Or perhaps life there huddles underground or beneath icy crusts, much like extremophiles in Earth's deepest caves or subglacial lakes. There's even a chance the planet is tidally locked, with one side perpetually scorched by its star and the other frozen in eternal night. But the twilight zone between these extremes could offer a precarious niche for life to cling. The real kicker, Proxima b's proximity means we might actually find answers. The James Webb Space Telescope has already trained its infrared eyes on this system, hunting for biosignatures, molecules like oxygen, methane, or even artificial pollutants that could hint at biological or technological activity. Detecting these signs won't be easy. Proxima b doesn't transit its star from our vantage point, so JWST must analyze starlight filtering through its atmosphere during close orbital passes. Even then, red dwarfs' flare activity can muddy the data, creating false positives or masking delicate chemical fingerprints. Future missions like the Habitable Worlds Observatory, slated for the 2030s, could bring sharper focus, directly imaging the planet and mapping its surface for oceans or continents. The search for life here isn't just scientific, it's philosophical. If life thrives on Proxima b despite the chaos of its star, it suggests the universe is teeming with life in even the harshest corners. And if it's barren, that might mean habitable zones alone aren't enough. Stars must also be calm enough to nurture life over billions of years. Either way, this pale red dot in the cosmos holds clues to one of humanity's oldest questions: are we alone? The answer might not come in a radio signal from distant stars, but in the faint spectral lines of a world so close we could almost touch it. The James Webb Space Telescope isn't just another instrument, it's a time machine, a cosmic chemist, and a planetary detective all rolled into one. Since its historic launch in December 2021, JWST has shattered expectations, peeling back layers of the universe we never knew existed. Take its very first deep field image, a speck of sky no larger than a grain of sand held at arm's length, revealing thousands of galaxies, some dating back to just 300 million years after the Big Bang. These aren't just distant objects, they're cosmic toddlers, caught in the act of forming stars at a rate that defies our models. One galaxy, Glass Z13, shouldn't exist according to conventional theories. It's too massive, too bright, too organized for such an early universe. Yet there it is, staring back at us from 13.4 billion years ago, forcing astronomers to rethink how galaxies grew up in the cosmos's infancy. But JWST magic doesn't stop at ancient light. It's also rewriting the playbook on exoplanets' worlds orbiting other stars. Using its infrared eyes, the telescope dissects starlight filtering through distant atmospheres, sniffing out chemical fingerprints like a cosmic bloodhound. In 2023, it detected carbon dioxide and methane in the atmosphere of K218b, a super-Earth orbiting a red dwarf star. These molecules, especially when paired with potential dimethyl sulfide detections, a gas on Earth produced only by life, raise tantalizing questions. Could this be a Hycean world, a water-rich planet with global oceans beneath a hydrogen-rich atmosphere? The data isn't conclusive yet, but it's a glimpse into JWST power to hunt for habitable or even inhabited worlds. Then there's the unexpected, chaotic stellar nurseries where planets form in violent bursts, like the Orion Nebula's protoplanetary disks, swirling with organic molecules like methyl formate and ethanol, the building blocks of life. Or the telescope's haunting images of the pillars of creation, where infant stars flicker to life inside towering columns of gas, their details sharp enough to count individual knots of collapsing material. Every observation feels like lifting a veil, revealing a universe far more dynamic and mysterious than we imagined. But JWST isn't the end of the story, it's the opening act. Enter the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. While JWST zooms in with laser precision, Roman will sweep the sky with a panoramic gaze, mapping billions of galaxies to trace dark matter's invisible scaffolding. Its coronagraph instrument will block starlight to directly image exoplanets, potentially spotting Earth like worlds in nearby systems. Together, these telescopes form a tag team, JWST as the scalpel, Roman as the wide-angle lens. And beyond them, concepts like the Habitable Worlds Observatory, a proposed mission to directly photograph and analyze atmospheres of exoplanets, could take us from detecting molecules to searching for definitive signs of life. What makes this era revolutionary isn't just the technology, it's the questions we're finally equipped to ask. Are we alone? How did the universe's first structures emerge? Every pixel of JWST data, every spectral line Roman records, is a clue in the greatest detective story of all time. And the most thrilling part, the next breakthrough could come any day, hidden in a stream of data waiting to be decoded. The universe isn't just showing us its secrets, it's daring us to keep looking. The Nancy Grace Roman Space Telescope isn't just another eye in the sky, it's a cosmic cartographer designed to map the invisible scaffolding of the universe with unprecedented precision. Slated for launch in 2027, this Hubble successor carries a mission so ambitious it could rewrite our understanding of reality itself. At its core, Roman is built to tackle two of cosmology's greatest puzzles: the nature of dark energy, the mysterious force accelerating the universe's expansion, and the search for exoplanets lurking in the glare of distant stars. But here's what sets it apart. While Hubble gave us stunning snapshots of celestial wonders, Roman will conduct a sweeping survey of the cosmos, capturing the equivalent of 100 Hubble Deep Field images, each revealing millions of galaxies in the same amount of time. Dark energy alone makes this telescope revolutionary. Imagine the universe as a loaf of raisin bread baking in an oven. As the dough expands, the raisin's galaxies move apart. Now picture the oven suddenly turning up the heat, causing the bread to swell faster and faster. That's dark energy's handiwork, and Roman aims to measure its effects across billions of years by studying subtle distortions in the light of ancient galaxies. This phenomenon, called weak gravitational lensing, occurs when massive objects warp space-time, bending the path of light like a funhouse mirror. By mapping these distortions across vast cosmic distances, Roman could reveal whether dark energy's strength has changed over time, clues that might point toward entirely new physics beyond Einstein's relativity. Yet Roman's ambitions don't stop at the dark universe. Its coronagraph instrument, a high-tech starlight blocker, will allow astronomers to directly image exoplanets orbiting nearby stars. Unlike transit methods that infer planets by their shadows, Roman's coronagraph could capture actual pictures of Jupiter-sized worlds, analyzing their atmospheres for molecules like water vapor or methane. But the real game changer, its ability to spot rogue planets, worlds untethered to any star drifting through interstellar space. These nomadic orbs, predicted to outnumber stars in our galaxy, might harbor subsurface oceans warmed by radioactive decay or tidal forces, raising the tantalizing possibility of life in the darkest corners of the cosmos. What makes Roman so groundbreaking is its dual nature. By day, it's a dark energy detective; by night, an exoplanet hunter. This versatility stems from its wide-field instrument, which can switch between surveying galaxy clusters and zooming in on individual planetary systems with ease. Future missions might build on its findings, but Roman's true legacy lies in the questions it will force us to ask. For instance, if dark energy's behavior defies current models, could our universe be one bubble in an infinite multiverse? And if rogue planets prove abundant, how many might carry the ingredients for life? As telescopes evolve, so does our cosmic curiosity. Roman won't just answer existing questions, it'll reveal mysteries we haven't even dreamed of yet. And in that uncharted territory between the known and the unknown lies the next great revolution in our understanding of existence. The universe, it seems, is always one step ahead, waiting for tools like Roman to catch up. The observable universe stretches an astonishing 46 billion light-years in every direction, a bubble of reality we can see, filled with galaxies, stars, and the faint afterglow of the Big Bang. But here's the cosmic twist: that's not the edge of existence. It's just the edge of what light has had time to reach us in the 13.8 billion years since the universe began. Beyond that horizon lies the unknowable, a region expanding away from us faster than light itself can travel, forever cutting us off from whatever lies past it. This isn't science fiction, it's the chilling consequence of cosmic inflation, the universe's explosive growth spurt in its first moments. So what could lie beyond our cosmic horizon? One possibility is simply more of the same: endless galaxies, stars, and planets stretching into infinity. A universe so vast it makes our observable portion seem like a single grain of sand on an endless beach. But some theories suggest wilder alternatives. Imagine a multiverse where our universe is just one bubble in a frothing sea of others, each with its own laws of physics. In some, gravity might be stronger, snuffing out star formation before life could arise. In others, matter might never have clumped into galaxies at all. This cosmic landscape emerges naturally from string theory, where tiny, curled-up dimensions dictate the rules of reality, and every possible configuration exists somewhere in the greater whole. Then there's the cyclic universe model, a dramatic alternative to the Big Bang. Picture two parallel universes colliding in higher dimensional space, their impact sparking a new cosmic cycle. Our universe expands, cools, and eventually contracts, only to collide again and rebirth itself in an endless loop. No singular beginning, no final end, just an eternal dance of creation and destruction. Or consider the holographic principle, which suggests our three-dimensional universe might be a projection from information encoded on a distant, two-dimensional surface. If true, the real edge of existence could be a shimmering boundary we'll never see or touch, a cosmic movie screen casting the illusion of depth, the most humbling thought. We may never know. The laws of physics as we understand them create an impenetrable veil beyond the observable universe. Light from those regions will never reach us, no matter how advanced our telescopes become. But here's the beautiful paradox. Even as cosmology reveals our cosmic isolation, it also hints at a reality so grand it defies comprehension. Whether we're alone in a single universe or one of infinite realities, the message is the same: we're part of something far greater than we can see. And perhaps that's the most profound lesson of all. The universe isn't just stranger than we imagine, but stranger than we can imagine. The true frontier isn't just space, it's the limits of our own curiosity. From dark energy stretching the cosmos at an accelerating pace to quantum particles communicating instantaneously across vast distances, these 42 phenomena shatter our everyday notions of reality. They reveal a universe where black holes warp time like taffy, where invisible dark matter weaves galaxies together, and where the very fabric of space might be a holographic projection from some distant boundary. Each breakthrough, whether it's the eerie silence of the Fermi Paradox or the explosive potential of gamma-ray bursts, doesn't just answer old questions. It peels back the curtain on deeper mysteries like layers of an infinite cosmic onion. Consider how far we've come. Just a century ago, astronomers debated whether the Milky Way was the entire universe. Now we're mapping the large-scale structure of existence, tracing filaments of dark matter that stretch hundreds of millions of light-years. Yet for all our progress, the more we learn, the more humbling the gaps in our knowledge become. Take the Hubble tension, the stubborn discrepancy in how fast the universe is expanding. This isn't just a minor accounting error. It could mean there's an entirely new force or particle influencing cosmic evolution, something beyond our current physics. Or ponder neutron stars, where a teaspoon of material weighs 1 billion tons. These stellar corpses defy the rules of matter as we know them, their cores possibly hiding exotic states like quark-gluon soup or even stranger forms of degenerate material. The beauty of these mysteries isn't just in their strangeness, it's in their connective power. Quantum entanglement might one day revolutionize secure communication, while asteroid mining could turn the solar system into humanity's stepping stone to the stars. Even the terrifying prospect of vacuum decay, where a quantum fluctuation could rewrite the laws of physics, reminds us that reality, as we experience it, might be just one precarious arrangement in an infinite landscape of possibilities. As telescopes grow sharper and probes venture farther, we stand on the brink of revelations that could redefine existence itself. Will we uncover microbial life in Europa's oceans, proving we're not alone? Could gravitational waves unveil hidden dimensions, or will dark matter finally show its face in some underground detector? The answers aren't just out there, they're waiting for the next curious mind to ask the right question. So stay hungry, stay wondering, and most of all, stay awestruck. The universe isn't just a collection of facts, it's an ongoing conversation between what we know and what we've yet to imagine. Drop your favorite cosmic head scratcher in the comments below, and don't forget to hit like and subscribe for more deep dives into the wonders of existence. The next revelation might be just one observation